Hello all, welcome to the GATE Academy, which is awarded as the fastest growing GATE institute in India and also awarded for best innovation in open and distance learning. So the GATE Academy has designed GATE score booster sessions to give a thrust to your preparation. So these sessions will contain questions which are of similar models which are frequently asked in GATE, as well as questions with traps. So the agenda of this session is to boost your marks. There are high chances that the questions which will be dealing here, they might be asked in GATE. Yes, Joker Lucky, hi everyone, good evening. Right? So there are high chances that you might get similar questions in GATE. So the the weightage of today's subject, that is electrical machines, in GATE is nearly 12 to 14 marks, right? So if you have solved all the previous repetitive models, there are high chances that you might get similar questions, which will fetch you a good number of marks from every subject. The GATE Academy has the score booster sessions for many other subjects as well, right? So let us not waste time and let us move on to the questions. So the agenda of this particular session is going to be like this. First, we are going to discuss a question on magnetic circuits. A question on magnetic circuits. After magnetic circuits, we'll be dealing with DC machines. A question from DC machines. Each question is framed so as to contain many gate-like questions. In each question, there are several gate-like questions. So each question is going to take a little longer than usual, but we'll be covering quite a many models, some many models in one particular question. Good evening, all. Good evening. Right. So after magnetic circuits, we'll be dealing with DC machines, and after DC machines, we'll be dealing with very good questions that are in transformers. All are good questions and frequently asked questions. After transformers, we'll be dealing with induction motors. Induction motors. And after this, we'll be dealing with questions from synchronous machines. Synchronous machines. So stay tuned to the video, stay tuned to the live session. You'll be solving entire machines. You'll be solving questions from entire electrical machines in just one particular session, which means this session is going to be very much helpful in boosting your score in GATE. So let us proceed with the questions. The first question you can see in the slide which I'm displaying here. So I'm just displaying the slide on the entire screen. It is a 100-turn coil fed with a fixed sinusoidal supply. A 100-turn coil fed with a fixed sinusoidal voltage source is used to construct a magnetic circuit as shown. The winding draws a current of 2 milliamperes to establish a flux of 100 milliwebers. If an air gap of reluctance 100 ampere turns per Weber is introduced in the magnetic circuit, the new value of flux and magnetizing current respectively are. So everybody please go through the question and try to understand what the viewer is asking, what the examiner is asking you. And tell me, just use the comment section to convey your ideas, how to approach at this particular question, how to solve this particular question. Tell me the ideas which come into your mind to solve this particular question. You can use the comment section. And the best part of this particular session is there will be a doubt solving session at the end. You can ask all your doubts with you can get them clarified with me at the end. We have a doubt solving session at the end of this session. So what is asked in the question? They've said they have fed this particular magnetic circuit Yes, N5. Very good. Very good. Lakshmi Narasimhan. I'll correct you wherever necessary. Yes, MMF is equal to phi into reluctance. Very good. Very good. So let us first understand the question. Let us just understand the question. What is given in the question? The MMF of this particular magnetic circuit is indirectly given by giving the number of turns. Number of turns are 100. Number of turns are 100. And the flux established in this particular magnetic circuit is 100 milliwebers. And the current drawn, the magnetizing current drawn to establish this much of flux is how much? 2 milliamperes. Therefore, what is the MMF? MMF, I'm just indicating by F. F is equal to N into I. This is equal to S into phi. You have these relations, right? MMF is equal to reluctance multiplied by flux, right? So from this relation, you can obtain the reluctance of this particular core. I'm just calling the reluctance of the core as S suffix core, right? You have to obtain the reluctance of this particular iron core. Therefore, S suffix core is equal to N into I upon phi. What is the value of N? N is 100. I is given to be 2 milliamperes upon phi. The value of phi is 100 milliwebers. 100 milliwebers. Therefore, the amount of this reluctance, you will get it as 2 ampere turns per Weber, right? So how many of you got the same? 2 ampere turns per Weber. 2 ampere turns per Weber should be the reluctance. So next, what is asked? If an air gap is introduced in this particular magnetic circuit, right? An air gap is introduced. What happens if an air gap is introduced? Can anyone tell me what happens if an air gap is introduced in this particular magnetic circuit? What happens to the magnetic circuit if an air gap is introduced? And the reluctance of air gap is given to be 100 ampere turns per Weber. Reluctance of the air gap is 100 ampere turns per Weber. An air gap like this is introduced. I'm calling reluctance of air gap as S air is equal to 100 ampere turns per Weber. And it is mentioned in the question, it is also mentioned to neglect the fringing effects. The flux which fringes, you have to neglect that. Stability, Rakesh, where does stability come from? Reluctance will increase and current increases as flux decreases. Very good. Very good. Right? So reluctance increases. See what happens to the magnetic circuit? Reluctance increases. If reluctance increases, see what should happen? The flux should decrease. If reluctance increases, see MMF you're supplying is constant. If reluctance increases, the flux should decrease, right? So what you're going to do is you will be adding the new reluctance and you are going to find out the new amount of flux. Flux is equal to N 100 multiplied by I. You will leave it as it is, that is 2 milliamperes, because I, the current drawn by this particular electric network, that depends on the parameters of this network, the resistance of this network, as well as the leakage reactance of this particular coil. Therefore, it is 100 into 2 milliamperes divided by S air plus S core, that is equal to 100 into 2 milli divided by S air is 100 plus 2, right? The flux, the amount of flux, if you are going to calculate, it will be around 1.96 milliwebers. Calculate करके बताना ये आ रहा है कि नहीं? Are you getting the same amount of flux or not? Just calculate and tell me. 100 into 2 milli divided by 102. You will be getting 1.96 milliwebers. Did everybody get this? Did you get phi as 1.96 milliwebers? Just answer in the comment section. Just calculate and answer in the comment section. Yes. Yes, Rajpudi Sai Seema, Sai Rama Raju. I'm sorry, Sri Rama Sudhamar Rajpudi. Your name is quite long, sorry. So the flux you got is 1.96 milliwebers. This is wrong. Many of you are saying current increases. Very well done. Very good. If you know this already, but many of you commit a mistake here. The flux will not decrease. A magnetic circuit excited by an AC source behaves in a different way when compared to a magnetic circuit excited by a DC source. The flux you got here is wrong, right? You're ending up with a wrong answer. If you go by the conventional approach that you use for DC magnetic circuits, you're going to end up with a wrong answer here, right? This is the trap. This is where the trap is, right? See what happens to the flux if we have introduced a reactance. So just tell me, to get answer for this particular question, tell me what is the EMF equation of a transformer or an induction machine or a synchronous machine. Assume the winding factors to be 1, right? Tell me the EMF equation of a transformer, a synchronous machine, or any particular induction machine's stator. You just take the stator of any induction machine, right? Tell me the EMF equation. Very good, Gaurav Vaidya. It is 4.445 m. Yes, 5 m. Maximum flux, peak flux, Fn, right? See, it is generally root 2 pi F phi max n. Phi max is the peak flux in the magnetic circuit. Peak flux in the magnetic circuit, right? So root 2 pi turns out to be equal to 4.44. Whenever you go calculations, you go with calculations in kilovolts, right? If the voltage is in kilovolts, then this should be root 2 pi. Leave this calculation to your calculator, because calculators are more accurate. Calculators give more accurate results than this 4.44, right? 4.44 is approximated. They'll give a more accurate result, right? So EMF is equal to root 2 pi F phi max n. Therefore, see here, EMF is being proportional to phi max. EMF is being proportional to phi max and F, that is frequency. EMF is proportional to phi max and frequency. See here, root 2 pi is constant. The number of turns, once you construct the magnetic circuit, the physical number of turns are always constant, right? N is constant. Therefore, E is proportional to phi max into F. What about the voltage V? See, the resistance and the leakage reactance are generally small. Therefore, the applied voltage is almost equal to the induced voltage. Applied voltage is almost equal to the induced voltage, because resistance of the circuit is very small, negligible. Then there is no drop in the resistance or leakage reactance. V will directly appear across the coil. Therefore, you can write this E proportional to phi max into F as V proportional to phi max into F. Therefore, you can say phi max is dependent on phi max. The peak flux is proportional to V by F. Peak flux is dependent on V by F. So as far as the voltage is constant and frequency is constant, it is given in the question. See, that is the reason why you should and you must read the question very carefully. You must read every inch, every centimeter of the question very carefully, right? See, it is already given. The magnetic circuit is excited by a constant AC source, constant voltage, constant frequency, right? Constant AC source. V and F are constant, fixed AC source, right? Therefore, phi max is proportional to V by F, which means the flux is not going to change until and unless you change V by F, right? So if you do not change V by F, if you keep V by F ratio constant, the flux is not going to change. Therefore, the flux you got here is wrong. The flux is going to be fixed. How much? The flux is 100 milliwebers only. To accommodate this amount of flux with high reluctance in the magnetic circuit draws more current in order to increase MMF. Yes or no? See, the reluctance has increased, which means if flux is constant, I has to increase because N is constant, right? So to make this happen, to make this amount of flux flow through the magnetic circuit, what should happen? The magnetizing current should be increased. So let us look at it. The new value of flux phi nu is same as the old value of flux, that is 100 millivebers. 100 millivebers. Therefore, use the relation mmf n into I is equal to S into phi. The reluctance has increased. The new value of reluctance is S core plus S air gap, that is 102. Therefore, I nu will be is equal to 102 multiplied by 100 millivebers divided by 100. Therefore, the new value of current I nu is equal to 102 milliamperes. The flux remains the same as the previous one. The flux remains same and the current increases, right? In an AC excited magnetic circuit, this is the scenario. This is the wrong answer, right? So tell me, what is the amount of magnetizing current, or else you can say what is the amount of no load current in a transformer in comparison with the full load current, right? Amount of no load current I naught in a transformer. Also tell me I naught in an induction motor, that is no load current in an induction motor, no load current in a transformer as well as no load current in induction motor. Yes, of course, Ravi Rao, it is very small. Tell me in percentage. Tell me in percentage. Yes, very good, Vishwas. It is 5% of full load, right? So Sai Rama Sudhamu Rajpudi, it is, yes, not 5 to 8%. It is 3 to 5% of full load. 3 to 5% of IFL, full load current. Whereas in the case of an induction motor, राकेश जी, आपने ऑलमोस्ट सही बोला पर थोड़ा सा करेक्शन है उसमें. In induction motors, it is 30 to 60% of full load current. The magnetizing current is 30 to 60% of full load current in an induction motor, whereas that in the case of a transformer is 3 to 5% of full load current. Why this huge difference? इतना ज्यादा difference क्यों है दोनों के magnetizing circuit में? Why this much of huge difference is there in the magnetic circuit of induction motor as well as transformer? Can anyone tell me? Can anyone explain me why this huge amount of difference? Very good. Very good. Sri Rama, I'll just call you in short by calling Sri Rama, okay? So Sri Rama, you're very good. That is because of the air gap in the magnetic circuit. See here, in a transformer, in the entire magnetic circuit, see the primary is placed here, primary winding is placed here, and the secondary winding is placed here, right? The magnetic circuit entire flux path is through the iron core. Reluctance of iron core is very less. Whereas in the case of an induction motor, yes, Siddiqui Mullah, very good. It is due to air gap. In an induction motor, see here, this is the stator. Stator has stator windings, which means stator will act as primary because you'll feed supply to the motor here. Right, supply is given through the stator. This is primary, and the rotor is like this. If you look at the path taken by the flux, see, it has to go through the air gap. It has to cross an air gap, which means the reluctance encountered by this particular induction motor, the reluctance encountered by this particular magnetic circuit is more when compared to the reluctance encountered by this, because of which you can see huge amount of no load current in an induction motor, right? So many of you know that it is 3 to 5% and this is 30 to 60% of full load current, but you don't know the reason. The reason is this. The reason is the air gap. Because of the air gap, the current has increased. So this is all about the question of magnetic circuits. Let us move on to the question on DC machines. The next question is on DC machines. Let us move on to the next one. So you can see the question here. The question is displayed on the screen. So just go through the question and give me the suggestions how to solve this particular problem. Just go through the question for a while and give me the suggestions. Tell me what approach should be used to solve this particular question. Note down all the given data in the question and go through each and every sentence given in the question very carefully. Right? Reading the question very carefully is what is very important. अगर आपने क्वेश्चन ढंग से पढ़ लिया तो समझ लो आपने आधा क्वेश्चन सॉल्व कर लिया. If you have read the question properly, you will be solving. It is equivalent to solving 50% of the question. So if you did not go through the last 45 days preparation plan, so browse through the channel, you will find a video called last 45 days preparation plan. In that, this point is mentioned to be very important. Reading the question is very, very important. Yes, Ravi Rao, very good. Making a circuit diagram, very good. Making a circuit diagram, of course, is important in understanding the question. Any other steps? This question on DC machines has 4 other questions. And this question covers a lot of topics. The first question is about the characteristics of the DC machine. The second question is about the value of M. This also belongs to the characteristics. And there are 2 more questions in this particular slide. You just go through that. The line current drawn by the motor, right? Motor and generator calculations, right? They are involved in this. And the third question is about speed control. The fourth question is about speed control, right? To control the speed of the motor, you have many methods like armature resistance control and shunt field weakening control, right? And the voltage applied, you can also control the voltage applied, right? There are all these methods. So 2 methods are directly covered in one particular question. 2 speed control methods. Yes, Vishwas, very good. T proportional to flux, that is torque proportional to flux. So I'm just reading the question and noting down the data here. So just go through the question as well as the data. I'm also reading it out. So just take a screenshot of the question if possible, and just you can just go through the question easily. Just take a screenshot of the question, right? The no load speed of a 200 volts DC shunt motor. See, it is given that 200 volts DC shunt motor, which means V is equal to 200 volts. 200 volts DC shunt motor is 3000 rpm, and not no load speed is equal to 3000 rpm, right? Next, what all data is given? It delivers a torque of 200 newton meters at a speed of 2500 rpm, right? Hello Krishna. At a torque of 200 newton meters, it is running at a speed, let us call it as n1 and call it as t1, corresponding torque as t1, and this as n1. is equal to 2500 rpm, right? By mentioning these things, they are just giving you information regarding the DC motor's characteristics, right? Next, the armature resistance and shunt field resistance are 0.1061 ohms. Armature resistance is 0.1061 ohms, 0.1061 ohms, and the shunt field resistance is 200 ohms. This resistance is 200 ohms respectively. And there is no power loss at no load. मतलब no load पे कोई power loss नहीं है, which means the 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 power loss when the machine is running at no load is zero, which means it does not draw any armature current while it is running on no load, right? The motor does not draw any armature current or else any load current, you can say, at no load, right? Even the load current can be termed as negligible. While, yes, Krishna, you have said about eddy current loss. No load, if no load losses are zero, constant losses are zero. Magnetic losses will also fall under constant losses only. Friction and windage losses and magnetic losses. Eddy current losses will also be zero, right? So next, while driving a load whose torque speed characteristics are given by N is equal to MT, the load driven by this particular motor has a torque speed characteristics like this. N is equal to XT, sorry. It is N is equal to XT, where N is speed in RPM and T is torque in Newton meters, and X is a arbitrary constant. X is an arbitrary constant. The machine runs at a speed of 2700 RPM. While driving this particular load, the machine is running at a speed of 2700 RPM. Let us call it as N2. It is 2700 RPM. So let us look at the first question. In the first question, it is asked to find out the torque delivered by the motor to the load is. So this is all about the information given in the question. And what is asked? The torque delivered by the motor to the load is. So many of you have said that is appreciable, right? We should be using these relations. EMF is proportional to back EMF in a motor, that is EB is proportional to speed multiplied by flux, as well as the torque is proportional to IA into flux, right? In spite of using this, there is a general relation which I generally deliver while delivering the concepts of DC machine. This general relation can be useful. This is K times of phi into omega. Omega is speed in radian per second. Omega is speed in radian per second, where N is speed in RPM, right? E is equal to K phi into omega. K will be called as machine constant, and T will be is equal to K phi into IA, armature current. IA is armature current in amperes. So just see here, E and T, you have got the relations between E and T. And Abhishek Kumar, you can just use the helpline number which is displayed above. You can just use the helpline number. So see, E is equal to K phi omega and T is equal to K phi into IA, right? So using these two concepts, you have to go through a number of mathematical manipulations. Using these two relations, you have to go through a number of mathematical manipulations, right? See, no load speed N naught is equal to 3000 RPM. If N naught is 3000 RPM, omega naught is equal to how much? 2 pi N by 60. Conversion of RPM into radians per second. This is equal to 2 pi into 3000 divided by 60 is equal to 100 pi. If you solve this, you will be getting 100 pi, right? Omega naught is equal to 100 pi. See, the no load losses are zero, which means there is no armature current flowing, or else no load current is flowing when the machine is running at no load, which means E naught will be approximately is equal to V. V is how much? 200 volts, or else you can call it as EB naught. If you want to mention it as back EMF, EB naught is equal to 200 volts. What is EB naught? EB naught is the back EMF, that is the voltage across this particular armature. This is EB, right? Back EMF is exactly is equal to 200 volts. So use the above relation and find out K phi. E naught is equal to 200 volts. That is equal to K phi into omega. What is the value of omega? It is 100 pi. This implies K phi will be is equal to how much? 200 by 100 pi. That is equal to 2 by pi. The value of K phi is equal to 2 by pi. Just don't simplify the calculations unless and until you require them. You can simplify at the last. Don't simplify them much. Right? You can save time by this. And always use gate calculator. Always use gate calculator while you are practicing. Right? Can we not simply use n is equal to xt relation and get? No, Sri Rama. See, the torque, the load torque as well as the motor torque, right? The motor and load are interacting, they are getting stabilized at a particular point, right? We cannot use a single relation to obtain the speed, right? And you don't know the value of x also. Even if you know the value of x, you might be getting it, but you don't know the value of x. Finding out the value of x is the next question, right? So see here, E naught is equal to this much. So what about the armature current? Armature current will be is equal to V minus EB divided by this armature resistance RA, right? So to find out armature current, you have to find out the resistance RA also, right? So use this relation, that is EB naught by EB1 is equal to N1 by N naught by N1. Sorry, EB1 by EB naught is equal to N1 by N naught, because E is proportional to N. The flux here is constant. Why? What is the reason? Because this is a shunt motor. Flux is equal to constant. You're not varying the shunt resistance. As far as you're not varying the shunt resistance, the flux is going to be constant only, right? If you vary the shunt resistance, then only the flux will be varying, right? So see here, EB1 by EB naught is equal to N1 by N naught. Therefore EB1 is equal to N1. What is N1? It is 2700 rpm divided by 3000 rpm multiplied by 200 volts. This you will get as 180 volts, right? When the motor is driving this particular load, the machine is running at 2700 rpm, which means the back EMF corresponding to this particular load is 180 volts, right? So 180 volts is the back EMF. And also find out IA. IA will be is equal to IA, let me call it as IA1. This will be is equal to V minus EB by RA. That is equal to 200 minus EB is 180 volts divided by RA. RA is given to be 0.1061. So if you solve this, you'll be getting a value of 188.5 amperes. 188.5 amperes. And use the relation for torque. Torque T is equal to K phi. Let us call it as T1, K phi into IA1, right? So K phi you already got it as 2 by pi. Therefore torque will be is equal to 2 by pi multiplied by IA1 is 188.5 amperes, right? This is equal to 120 Newton meters. So if you calculate, you should get 120 Newton meters. So see here, approach is quite lengthy. And one more thing is, you cannot, you might be making a mistake while doing these many calculations, right? Yes, Lakshman, very good. The answer is 120, of course. You got the answer, of course, but look at the time you have taken. See, for me, I know the approach directly, so that without any trial and error, I just arrived at the final value, right? Arrived at the answer. But when you know the approach in your examination, you'll be in a tensed mood. Whether in that particular tensed mood, you'll not be remembering these many relations. You'll not be remembering these many relations. इतने सारे relations याद नहीं रहेंगे और बीच में गलती करके बैठ जाएंगे, right? You will end up with the wrong answer again, right? So try to cut short the procedure as much as possible. जितना हो सके उतना कट शॉर्ट करो. Try to cut short as much as possible so that you can arrive at the answer, the final answer, in a very easy manner. See, in this particular question, IA, is it asked? IA is not asked, right? In the first question, let us think the first question is only asked in the GATE exam. IA is not asked, right? What about the other things? K5, this is also not required, right? So EB1, this is also not asked. You are calculating many things which are not asked to find out the final thing. This is the problem in DC machines. Many people use such approaches and they fail to they fail to get an accurate final answer. That is the problem, right? I'll be telling you a more intuitive, a more understandable, a more easier graphical approach so that you can arrive at the answer very easily. You can arrive at the answer at with ease, with very ease, right? So I'm just erasing this. Just note it down or else take a screenshot so that you can note down it later, right? I'm just erasing the board. So taking the screenshot. See, by giving this particular data, what is that the examiner wants to give you, wants to convey? The examiner wants to give you the characteristics of this particular equation. The examiner just wants to tell you about the characteristics of this particular equation, right? Yes. The examiner is giving you the characteristics of this particular equation, right? So the no load speed is given, the speed at a particular load is given, and the speed of the machine while driving this particular load is also given, right? So see here, just plot the characteristics. This is torque in Newton meters, this is N in RPM, torque in Newton meters, and N in RPM, right? The no load speed is how much? No load speed is 3000 RPM, and the full load speed, it is not given to be full load speed, but you can say the speed at a particular load. Speed at a particular load is 2500 RPM. So these are the characteristics of a DC shunt motors, the speed torque characteristics of a DC shunt motor, right? So you have studied this many times. You have studied the characteristics of DC shunt motor, induction motor, everything, but you will not use them in the numericals. What is the use, right? So you, until and unless you use the characteristics, right? Until and unless you use the characteristics, these characteristics are useless to you. Yes or no? Characteristics are useless. So see here, the characteristics, the torque speed characteristics of the load are given as TL is equal to, or else you can say N is equal to some X times of T. If you get the characteristics, the equation for characteristics of this particular DC machine, and you solve both the straight lines, you will get this point. This point is nothing but the operating point of the machine, right? The speed at which the machine is operating, that is found out easily. Also the torque of the machine, right? Speed at which the machine is operating, that is already given. What is the speed? This is 2700 rpm, and you have to find out this torque, right? Now it is very easy to find out the equation of this particular straight line, yes or no? You can use y is equal to mx plus c. See, this equation is given in y is equal to mx format. Y is equal to mx format, right? So you can find out the equation of this using the format y is equal to mx plus c. Y is equal to mx plus c. What is on y axis? On y axis it is n, that is speed. N is equal to slope. What is the slope? Look at the slope. See, it is a negative slope. Quite evident from the equation of the straight line, it is a negative slope, right? So the y-intercept is 3000. Y-intercept. The straight line intersects the y-axis at y-intercept, which is 3000. So the slope is, it decreases, the speed decreases by 500 within 200 Newton meters. The speed decreases by 500 within 200 Newton meters, which means minus 500 by 200 into t plus 3000. This is the equation, right? Characteristics of DC motor in the form of a mathematical equation, right? So if you just solve these two equations, you should be getting the operating point, right? But a parameter of the operating point is given, that is the speed with which the drive is rotating, that is given, right? You have to find out the torque. So put this particular value of speed in this. Put this particular value of speed in this. So someone said it previously, torque is given to be is equal to xt. So they asked me, sir, can we put 2700 in this and can get torque? Because you don't know the value of x, you cannot get, right? So only if you know the value of x you can get, otherwise you cannot get, right? So you just substitute 2700 in the place of n. It is 2700, that is equal to minus 2.5. If you simplify 500 by 200, it is 2.5, right? Plus into t plus 3000. So calculate and tell me the value of torque. T is equal to 2700 minus 3000 divided by minus 2.5, right? So it is 300 by 2.5. What is the value you're getting here? It is again 120. Very good. Value of torque is 120 Newton meters. See, one thing you need to observe here. To explain to you, I've just drawn this much and at least this much lengthy. Otherwise, you need not draw this, right? You need not even draw this, and you can just find out the value of t is equal to 120 Newton meters just by solving these two equations. From the given data, you can directly construct the characteristics of DC machines in mathematical equation, right? So you just solve this with this, you'll get the final value. That is very simpler method. See, if at all you're learning characteristics, I've seen nowhere that students or any other institutes are using the characteristics to obtain numericals, right? Numericals solve करने के लिए कोई use ही नहीं कर रहे. What is the use if you do not use the characteristics in solving the numericals? In fact, practically all while designing all the motors and all, these are what are used because they give more information. Just by looking into that, you get a lot of information, right? So calculations practically generally are done this way, right? Not by finding that equation, this equation, and multiplying that with this, right? That will create a lot of confusion. If you have 10 equations and you have a lot of paperwork, you'll end up confused, right? So just try to go by the smartest method. This is the smartest method to solve this particular question. In fact, we have got a question in 2015 based on this kind of concept. In that particular question, even RA is not given. It is very tough to find out the value of torque, or else I think speed is asked in that. Speed is asked, torque is given, right? It is very tough to find out the value of speed This is given in gate 2015, not this. A question similar to this, in that RA is not given. If RA is not given, you cannot find out IA. If you go by the conventional approach, then it becomes very difficult. And this method solves it in a second, right? So very simply, this method will solve that particular question in a second, right? So that is the importance of this particular question. So let us move on to the second question, the second part of the question in DC machines. What is the second part? So just go through the second part. The value of M is asked. The value of M. I'm sorry, it is just a typing mistake. M, not is it is not M. The value of X. You need to find out the value of X. The value of X has to be found out, right? See, you know speed, you know torque, right? You know speed at a particular point, that is 2700, and torque at a particular point, that is 120 Newton meters. You can get X easily, right? X is equal to N1 upon T1. That is equal to what? 2700 divided by T1. The value of T1 is 120. X is equal to 2700 divided by 120. Tell me the value. Can anyone tell me the value? Just calculate and tell me the value. Very good. It is 22.7, 22.5. The value of X is 22.5. Very simple. See, one mistake students may do here. See, this particular value of X, they describe the point on this characteristic, right? So if I have given a speed some which is not lying on this particular torque speed characteristics, right? That speed is lying on these characteristics, let us say, right? Then you cannot find the value of X by finding out the ratio of N upon T, right? You cannot find in that way. You have to see, you have to check the characteristics of load are this, right? If the speed lies on this particular, the speed and torque corresponding to this load are given, only then you can calculate X by finding out the ratio, otherwise you cannot, right? So please do not do such kind of mistakes. They are, you cannot call them even mistakes, they are blunders, right? So let us look at the next question. The line current drawn by the motor. What is the amount of line current drawn by the motor? That is asked. See, you have gone through the circuit, right? The circuit of the DC motor you have gone through, and you have to find out IA. IA you have found out in that previous method, right? Which is not asked in the first question. If it is asked, you can go by that method, but it is not asked there. See, you have to find out IA. IA is equal to V minus EB upon RA, right? So V, you know, that is 200, and EB you have to find out. EB is EB, that is back EMF corresponding to this speed, back EMF corresponding to 2700. So back EMF corresponding to 2700, EB1 is equal to N1 by N2 multiplied by EB0. That is equal to, this is not N2, N0, right? 2700 divided by 3000 multiplied by 200. You've already done this in a different procedure. You got it as 180 volts. Therefore, 200 minus 180 volts divided by how much? Divided by the value of RA is 0.1061. Right, it is 20 divided by 0.1061. You will be getting a value of, just tell me what is the value. The value is 188.5 amperes. Right, the value of IA is 188.5 amperes. Sri Rama, do not worry. If you fail to note down this, you will be having the recorded version also, right? Please do not worry, but try to be alive, try to be live in this particular session, because I'll be attending your doubts. Yes, very good, thank you. 188.5. So let us go by the next question. The next question is about speed control. To obtain a speed of 2500 rpm by maintaining the armature current to be same as the above value, you have to note here armature current is same as the above value, right? Which means armature current is constant at 188.5, right? It might be the rated current, right? The one who is operating the motor, he might be wanting that he don't want to increase the current beyond the rated current, right? If the current increases beyond the rated current, heating in the machine will be very much very high, and it may just get destroyed. The machine may get destroyed, right? So for maintaining the armature current to be same as the above value, the resistance is needed to be added in the armature and shunt field circuit respectively are, right? You have to add resistances in armature as well as shunt field circuits, right? Anjali Kumari, I'm sorry, I should use N2 here, that's it, right? So all values corresponding to this speed are asked. That is the reason why I should use N2. Just correct it. So let's now go by the next question. See, to decrease the speed, what you have to do? You have to increase armature resistance, right? To increase the speed, you have to increase the shunt field resistance. For above rated speed operation, you will use field flux weakening method, and to obtain below rated speed operation, you have to use which method? You just have to use simply the armature resistance method, or you can say armature voltage control method, right? To obtain below rated speeds. So if you use armature voltage control method alone or else armature resistance control method alone, what happens is armature current decreases, right? Armature current will decrease. If armature current decreases, torque which is proportional to the product of armature current as well as flux, torque which is proportional to armature current and flux, right, this will get decreased, right? So without disturbing this, you have to maintain the armature current constant, and you have to just adjust the value of armature resistance and shunt field resistance. So let us go through the question now. So you can write EB2 by EB1 or else EB naught. EB2 by EB naught is equal to N2 phi 2 by N naught phi naught. Let us call the flux at phi naught to be some phi, right? Flux when there is no resistance introduced is some phi, right? So EB2 by EB naught, therefore EB2 will be is equal to N2. What is the speed? You have to find out at a speed equal to 2500 rpm. It is 2500 by N naught. N naught is 3000 multiplied by the flux, right? So this is some phi dash, let us say this is phi. So you have to find out the ratio of phi dash and phi. You before finding out EB2, to find out EB2 you require the ratio of phi dash and phi. So let us say phi dash. How will you get phi dash? You will be getting phi dash if you get the ratio of armature current previously and the ratio of ratio of shunt field current previously, and the ratio and the current shunt field current, I'm sorry, the previous shunt field current and the present shunt field current, that is ISH dash by ISH 1, right? So see here, you should find out the ratio of T2 by T1. T2 by T1 is ratio of IA2 by IA1 multiplied by phi 2 by phi 1, right? So the second torque at 2500 rpm, torque at 2500 rpm you can say, right? And to find out the torque at 2500 rpm, you have to find out the previous torque as well. I'm sorry, sir, N1. See, don't go by this nomenclature. I won't be remembering the nomenclature exactly, right? So just remember the nomenclature as the speed or torque corresponding to this particular speed, or else the flux corresponding to this particular speed. Now we have to bring the speed to 2500 rpm. This is our motto, right? So we have to bring the speed to 2500 rpm, which means you have to find out the torque corresponding to this 2500 rpm. Torque corresponding to 2500 rpm is given by the load torque characteristics. T is equal to x into n is equal to x into t. N is equal to x into t. Therefore, T is equal to 2500 divided by x, that is 22.5. 2500 divided by 22.5, you will be getting a torque of 111.11 Newton meters. Right? So it will be confusing to remember which torque belongs to whom and all, right? So that is the reason why this got fumbled here. Right, so it is n is equal to x times of t. You will be getting a torque of 111.11 Newton meters. Right, so now if torque is proportional to Ia into phi, therefore T2 by T1, or else let us say this T2 is the torque corresponding to this particular speed. T2 is the torque corresponding to this particular speed, that is 2500, divided by T1, the torque which you know previously. The torque which you know previously was how much? You have calculated, that is 120. Therefore, T2 by T1 is 111.11 divided by 120. This is equal to Ia2 by Ia1. Ia is maintained constant, armature current is maintained constant, which means this gets cancelled, right? It is simply phi 2 by phi 1. So this is what is you require, right? You require the ratio of phi 2 by phi 1, the new value of flux to the old value of flux, right? So phi 2 by phi 1, that is equal to phi dash upon phi, which you have used here, right? That is equal to 111.11 divided by 120. Tell me what is the value of this. Tell me what is the value of this. Meanwhile, I'll just erase the board here. See, that is the problem when you go by a lot of equations. If you have a lot of equations, you won't be remembering the nomenclature, which is n2, which is n1, which is n0, which is n1, which is n3, right? You won't be remembering the nomenclature. So try to go with as less number of calculations as possible. Here it is unavoidable. That is the reason why we are going here, right? So the value of phi 2, or else you can say phi dash is equal to 0.9259 times of phi. If you want, you can use this nomenclature also. Phi 2 is equal to 0.9259 times of phi, right? So you require this, you got it. So you will get EB2. This will be is equal to 2500 by 3000 multiplied by phi 2. This is 0.9259 times of phi divided by phi. This phi and phi gets cancelled. You will get a value of EB2. Tell me the value of EB2 by calculating. Just calculate and tell me the value of EB2. Back EMF. Back EMF for a speed corresponding to a speed of 2500 rpm, right? 2500 rpm is the speed, and back EMF corresponding to this. You have to find out. Tell me the value just by calculating. What is the back EMF value? Yeah, sorry. This is EB2 by EB0. Ratio of back EMFs is N1 phi 1 by N2 phi 2. So this should be multiplied by, to get the value of back EMF, you should multiply this with EB0, right? Therefore, 2500 by 300 multiplied by 0.9259, right? Therefore, EB2 will be is equal to this entire thing multiplied by EB0. EB0 is how much? 200. Yeah, right. 154.31. Did you get 154.31? Very good. It is 154.32. 154.32 volts. Back EMF EB2 is equal to 154.32 volts. Right. So once you got the value of back EMF, you can get the value of new speed, right? So what is asked is the value of armature current, sorry, the value of armature resistance to be inserted in the circuit, in the armature circuit, to maintain the same amount of armature current, right? So armature current IA is V minus EB. Now it is V minus EB divided by armature resistance plus some additional resistance, right? So some additional resistance, I'm calling it as R dash, right? Armature current should be maintained constant. How much? It should be 188.5 amperes, right? So it should be 188.5 amperes. And uh, see, the external resistance which you have added, EB value you got here, it is 154.32 divided by this, you will get RA plus external resistance. 188.5 amperes is equal to RA plus R dash. RA plus R dash. Therefore, RA value you already know it, 0.1061, right? R dash will be is equal to 20 divided this 200 minus 154.32 divided by 188.5. You'll be getting some value of this. It is 0.2423, right? Therefore, R dash will be is equal to 0.2423 minus 0.1061 minus 0.1061. You will get a value of 0.1362 ohms. Very good, Sri Rama. It is 0.1362 ohms. The value is 0.1362 ohms, right? External resistance should be this, external resistance of this much should be inserted in armature circuit, right? So along with this, you have to insert an additional resistance in the shunt field circuit as well, right? So not only this, you have to insert one more resistance that is in the shunt field circuit, right? If you add up some shunt field resistance, then the speed is the armature current is going to be maintained at 188.5 amperes, right? Armature current will be maintained at 188.5 amperes. To calculate the value of additional shunt field resistance, you already have the value of the new value of flux upon the old value of flux, that is phi dash upon phi, which you have calculated, right? So phi dash upon phi is 0.9259, you got 9259. Therefore the new value of flux phi new is equal to 0.9259 times of old value of flux, right? So old value of flux is depending on the, sorry, new value of flux is depending on the old value of flux, that is 0.9259 times of old, becoming, Siddiqui Mullah, this is not one question. That is what I've said at the starting, right? This is not a single question. There are several number of questions added in a single question, right? So some questions will be long and they will give you, they will fetch you 2 marks in gate. Of course, they'll ask little long questions also. They'll fetch you 2 marks, right? So see here, ISH new value of shunt field current. ISH new is equal to 0.9259 times of ISH old. So you must be knowing ISH old, right? So the shunt field resistance RSH is given to be how much? It is 200 ohms, and the voltage across this, the voltage at which this is operated, V is equal to 200 volts. Therefore, ISH is equal to V divided by R, that will be is equal to 1 ampere. ISH old, the old value of shunt field current is 1 ampere. If the old value is 1 ampere, what is the new value? New value, that is ISH new, is equal to 0.9259 multiplied by 1 ampere, which means 0.9259 amperes. So this is the final answer, right? So sorry, this is the new value of ISH. To get this much of ISH, the amount of additional resistance that you should insert in this, the question asked is about the amount of shunt resistance to be added, right? So if this is the new value of ISH, ISH is equal to V by RSH plus external resistance in this shunt field. I'm calling it as R double dash. R double dash. This is equal to, see, this is equal to 0.9259 amperes, which means V divided by, V is 200 volts, 200 volts divided by 0.9259 amperes is equal to RSH plus R double dash. RSH plus R double dash. So you will get the value of RSH plus R double dash. Tell me the value. The value of 200 divided by 0.9259. Therefore, R double dash will be is equal to the value you got minus 200, right? The value you got, just tell me the value, and this minus 200 ohms. The value of R double dash should be 16.006 ohms, right? This is the final answer, right? Not the shunt field current is asked, the shunt field current is not asked, only the value of external resistance that should be added, this is asked, right? So the value you got here is how much? 216. Very good. 216.006, right? 216.006 minus actual shunt resistance, you will get the value of additional resistance, right? So this is the process. See, if you look at the question, characteristics are covered in the first question. In the second question is also about the characteristics, right? The third one, line current, motor calculations, how you calculate current and all, right? So the armature current you got is 188.5 amperes. And what about the field current? Field current, ISH is equal to 1 ampere. There is a danger that you might commit a mistake here. What is the mistake? Line current, IL is equal to IA, armature current plus shunt field current. How much is the armature current? That is 188.5 amperes plus 1 ampere. 1 ampere. So the result should be is equal to, the value should be is equal to 189.5 amperes. It should be is equal to 189.5 amperes, right? Line current should be is equal to 189.5 amperes. As soon as you get the armature current, if you do not read the question properly, you'll end up putting 188.5. You should put 188.9, right? The correct answer is 189.5. That is the correct answer for the third question. And the fourth question is about speed control. You have seen the procedure. You must insert this much of additional resistance in the armature circuit, that is 0.1362 ohms in armature circuit, and 16.006 ohms in the shunt field circuit, so that you will be ending up with a current same as the previous case. Armature current should be same as the previous case, that is 188.5, right? So I can understand the question is a little lengthy, but I have tried to cover as many concepts as possible in a single question, so that you will get, just by studying this particular question, just by solving this particular question, you'll be most benefited in GATE 2020, right? In question it is given n is equal to tx. Is this mean torque proportional to speed? Yes, Nagasrikar, N is equal to Tx. N is equal to x times of T. This means that speed is proportional to torque. Exactly. Speed and torque are proportional to each other. Right? So let us look at the next question. The next question is about transformers. So I'm just putting it on full screen. Just go through the question. The short circuit test data and open circuit test data of a transformer, of a single phase transformer, are given. Short circuit and open circuit test data of a single phase transformer is given. Right? The rating of single phase transformer is 300 kVA, 11 kV by 400 volts, 50 hertz distribution transformer. Right? It is a distribution transformer. And after giving the data, the percentage voltage regulation at full load is asked. You have to find out the percentage voltage regulation at full load. So all of you just use the comment section to tell the formula of voltage regulation, formula which you use to find out voltage regulation. The first question is about voltage regulation. Right? Which formula you will use to find out voltage regulation? What is the formula to find out voltage regulation? Yes, Lakshmi Narayan, very good. It is R per unit cos phi and X per unit sin phi, right? And there is one thing that is not mentioned in the question, that is phi should be is equal to 0.8. Cos phi should be is equal to 0.8. So correct the question as the percentage voltage regulation at full load 0.8 lagging power factor is. Power factor is 0.8 lagging. So just correct the question as the percentage voltage regulation at full load 0.8 lagging power factor. Right. So yes. What is the value of voltage applied while performing the short circuit test? While performing the short circuit test, the value of voltage applied is 210 volts. See, it is given that LV is shorted. Can anyone tell me what is the reason why we short LV? लो वोल्टेज वाइंडिंग को ही क्यों शॉर्ट करते हैं? What is the reason that we short only LV only? Why not HV? Why don't we short HV while performing short circuit test on a transformer? Can anyone tell me? Yes, Rakesh, be very good. R per percentage R cos phi plus percentage X sin phi. This is also correct. Right. So tell me, someone please tell me what is the reason why we have to short only the LV, that is low voltage side, while performing short circuit test, and why not HV? And while performing open circuit test, only HV is open circuited. Why not LV? Only HV is open circuited. Why not LV? Yes, Nagasrikar, rated current is less on LV side, of course. Saturation is one reason. No, Siddiqui, that is not the correct reason. Less voltage is required to produce rated short circuit current. No, Sri Rama, not less voltage. If you short circuit LV, you have to provide voltage at HV side. You require more voltage, in fact. Right. As compared to the short circuit test performed on LV side, you have to provide more voltage, but that is not at all a valid reason. That is not a valid reason. Yes, Lakshmi Narasimhan, high value of current flows in the LV when compared to HV, right? See, LV current is more when compared to HV current. So if you short circuit HV to LV, you have connected the source. To this LV, you have connected the source. Source has certain impedance, right? So to LV, you have connected the source, which means this LV is drawing current from the source. Your supply from the supply voltage, LV is drawing the current. If LV draws current from the supply, right, what happens is it draws more current when compared to the current drawn by this HV side, right? HV side के comparison में LV ज़्यादा current खींचेगा if more current is drawn, right? See, practically do not short the transformer just by connecting to a direct rated supply, right? I'm taking this source as low voltage supply. Low voltage is provided by using auto transformer, right? Low voltage is provided by using auto transformer. So when you short the supply, what happens is LV draws its rated current. If you draw higher amount of current from the supply, what happens is the terminal voltage decreases. There is a drop in terminal voltage, which is called as loading effect. This is called as what? Loading effect. So what happens to the terminal voltage? This terminal voltage will drop. V terminal voltage will drop. So what is the disadvantage? See, while you start an induction motor, what is the starting current in an induction motor? In an induction motor, starting current is nearly 6 to 7 times of full load current. 6 to 7 times of full load current. It is equivalent to operating 6 induction motors at a stretch, right? So it draws a huge amount of 6 to 7 times of full load current. If this huge amount of current is drawn, you can observe a voltage dip, because of which lights dim for a while. When you start an induction motor at your house, what happens? Lights will dim for 2 seconds, 3 seconds, right? Later on, the lighting is again restored, right? The reason for this dim is decrease in the terminal voltage, right? In the manufacturing industry, while you're testing your transformer, if the terminal voltage decreases, terminal voltage drops, the parallelly operating machinery in your manufacturing plant, they will get disturbed. There is a chance that motors, the conveyor belts motors and every other motors in your process industry, they might get shut down, right? So that will interrupt the parallelly operating apparatus. So in order not to interrupt the parallelly operating apparatus, we generally short the LV side and provide supply to the HV side, so that HV side generally draws less current as compared to LV side. And the reason for opening HV is, see, for measuring things on HV side, you require very robust equipment, right? At high voltage, in open circuit test, you provide rated supply to the transformer. When you provide rated supply to the transformer, what happens is, see, let us say you have some kind of transformer like this, 11 kV by 200 volts or else 400 volts transformer, right? So this is more 11 kV equipment, 11 kV ammeters, 11 kV voltmeters, 11 kV wattmeters, they are more costly when compared to 400 volts wattmeters, 400 volts ammeters, 400 volts voltmeters, right? Voltmeters or ammeters operating at low voltage are cheaper, and voltmeters and ammeters operating at 11 kV, that is high voltage, they require more insulation and hence they are costly, right? So to be cost effective while performing tests, we generally open HV test, HV side while performing open circuit test, and we generally short the HV side while performing short circuit test. Oh, sorry, we generally short LV side while performing short circuit test. LV is shorted, right? So let us now go through the question. The voltage applied while performing short circuit test is how much? It is 210 volts. First of all, write down all the data given corresponding to the transformer. The data given is the rating of the transformer is 300 kVA and the voltages are 11 kV by 400 volts, right? It is a 50 hertz, 11 kV by 400 volts, 50 hertz transformer. Percentage voltage regulation at full load, 0.8 power factor is asked. Just remember this, there is a correction in the question, that is cos phi is equal to 0.8 lag, right? Percentage voltage regulation at 0.8 lagging power factor, right? So to find out voltage regulation, you may use this formula. Voltage regulation is equal to R per unit cos phi plus or minus X per unit sin phi multiplied by 100, right? R per unit cos phi plus or minus X per unit sin phi multiplied by 100. This plus is for lagging power factor loads and minus is for leading power factor loads. You'll use negative here for leading power factor loads. You can also use one more formula, right? From this particular formula only you got this formula. You can also use VR is equal to Z per unit cos theta equivalent minus phi. Z per unit cos theta equivalent minus phi, right? So you have to find out the per unit impedance of the transformer multiplied by cos theta equivalent minus phi. So how can you find out the per unit impedance? You can find out the per unit impedance from the open and short circuit test data given to you, right? So theta equivalent, once you find out R per unit and X per unit, you can find out theta equivalent. Theta equivalent is cos inverse of R per unit upon Z per unit. I'll show you how, right? So find out Z first, the impedance. See, the voltage applied during short circuit test is 210 volts. V is equal to 210 volts and the current that is flown is 15 amperes. 15 amperes. Therefore, Z will be is equal to, that is Z equivalent will be is equal to V divided by I. I'll give you the equivalent circuit also. Z equivalent will be is equal to V divided by I, that is 210 by 15. Tell me the value. What is the value of 210 by 15 you're getting here? Just calculate and present your answer in the comment box. Just calculate and tell me the answer. The value of Z equivalent you're getting. Very good, Lakshmi Narayan. It is Lakshmi Narsimhan. It is 14. Yes. Yes, it is 14. Z is equal to 14 ohms. Right. So the copper loss inside the machine, that is also given. What is the copper loss? It is 2574 watts. WCU, I'm indicating copper loss with WCU, that is 2574 watts. So copper loss will be is equal to I square R equivalent. Yes or no? See, what is the equivalent circuit of the transformer? This is R equivalent. This is J times of X equivalent. And through the short circuit, through this particular short circuit, the short circuit current of 15 amperes is being flown, right? 15 amperes is adjusted by adjusting the voltage, right? So this is Z equivalent. So you have to find out the value of R equivalent. The wattmeter reads the copper loss, right? So I square R equivalent, IISc square R equivalent is equal to the copper loss. What is IISc? That is given to be 15 amperes. Therefore, you can find out R equivalent from this. That implies R equivalent will be is equal to 2574 divided by 15 square. 2574 divided by 15 square. Tell me the value of R equivalent in ohms. Equivalent resistance in ohms. What is the value? Just calculate and tell me. Very good. Very good. It is 11.44. R equivalent is equal to 11.44. So if at all you need X equivalent, you can calculate X equivalent also. How can you calculate X equivalent? X equivalent will be is equal to under root of Z equivalent squared minus R equivalent squared. Right? See, since Z equivalent is equal to under root of X equivalent squared plus R equivalent squared. So you can calculate in this way. X equivalent is equal to 8.07 ohms. If you calculate X equivalent, you will get 8.07 ohms. See, the things you require are power factor angle phi, that is given. See, power factor angle phi is given by cos inverse of 0.8. Z per unit, you can find out Z per unit. If you, as soon as you find out the base value, you can find out the value of Z per unit, right? Base value of impedance, Z base is equal to V square by S base, VB square, base voltage square upon base KVA. What is the base voltage? Base voltage is nothing but the rated voltage. Yes, 2.70. Lakshmi Narasimhan, you got it wrong. There's a mistake in your question, in your answer. Right. So just check for calculation errors. See, the base voltage is the rated voltage. Right. What side you are performing this test? Right. You have connected the supply to which side? LV is shorted means HV is connected to the supply side. Right. The HV side voltage is 11 kV square. Right. If you get impedance on the LV side, see, if you refer this HV side impedance, this Z per unit, X per unit and R per unit, if you refer them to the HV side, so if you refer them to the LV side, you can use LV voltage. But the impedance you got is the impedance on HV side, HV winding of the transformer. Therefore, it is 11 kV squared upon S base. What is the value of S base? Base KVA, that is 300 K. 11,000 squared upon 300,000. So tell me, what is the value of base impedance? Base impedance is, can you calculate and tell me the value of base impedance? 403.33. Very good, Sri Rama. It is 403.33 ohms. Base impedance is 403.33 ohms. Therefore, Z per unit is equal to Z actual. What is the value of Z actual? Actual impedance is 14 ohms divided by 403.33 ohms. So what is the value of Z per unit you are getting? Z per unit is 0.0347. Are you getting the same? Z per unit should be is equal to 0.0347. Very good, Sri Rama. The calculation is, the value of Z per unit is 0.0347 ohms. Sorry, per unit, there is no unit. So 0.0347 per unit. Right? So this is the value of Z per unit. So you have to find out theta equivalent. Theta equivalent means the impedance angle. Impedance angle of the equivalent impedance. To find out impedance angle of the equivalent impedance, just go by the impedance triangle. The impedance triangle is like this: J times of X equivalent. This is R equivalent, right? R equivalent and J times of X equivalent. This will be is equal to Z equivalent, right? The angle here, this angle is nothing but theta equivalent, right? Therefore, theta equivalent is equal to cos inverse of R equivalent upon Z equivalent. Cos inverse of R equivalent upon Z equivalent. You're getting it as 54.7998. 54.7998. This is the angle. right? Yes, you can use that formula, of course, regulation. Yes, Vishwanath, you got almost the correct answer, right? So if you use this particular value of theta equivalent in this particular equation, that is voltage regulation will be is equal to VR will be is equal to how much? Z per unit 0.0347, 0.0347 multiplied by cos theta equivalent 54.7998 minus cos inverse of 0.8. You'll be getting some 36.36 something, right? So cos inverse of 0.8. So this value is going to be 0.9514. Both these things multiplied by 100 will give you percentage voltage regulation. There is no space here. I'll just write it here. In this column, I'll write it. Percentage voltage regulation VR, red might not be visible. VR is equal to 3.3%. If you just simplify this, you'll get a value of 3.3% approximately. So this is the full load voltage regulation. Voltage regulation at full load 0.8 lagging power factor. This is the value of voltage regulation at full load 0.8 lagging power factor. So if I have asked you about the voltage regulation at half load, right? If I've asked you voltage regulation at half load, what you will generally do is you may either use the bigger one, the big formula, right? So you have this formula, right? VR is equal to I into R equivalent cos phi plus or minus I into X equivalent sin phi divided by V, right? Let us say full load current is 100 amperes. Full load current is 100 amperes. If IFL full load current is 100 amperes, half load current will be I half load. Half load current will be is equal to 50 amperes, right? If I ask voltage regulation at quarter load, that is quarter load means one fourth load, one fourth of full load, one fourth of full load is 25 amperes, like that. So you can use the value of I and you can find out the value of voltage regulation, or else after getting the voltage regulation you can find out the induced voltage or terminal voltage at any particular load just by using these simple formulae, right? So the easiest approach is going by this, because if you know this Z per unit cos theta equivalent minus phi, you can easily approach at maximum voltage regulation, minimum voltage regulation, and zero voltage regulation also, right? So let us look at the next question. The next question is about efficiency. It is asked to find out the efficiency at full load 0.8 lagging power factor, right? Efficiency of the machine, efficiency of the transformer at 0.8 lagging power factor and full load. So how will you solve this particular question? How will you obtain the efficiency? Can anyone tell me? Efficiency is output power by, efficiency is the ratio of output power to which power? See, as soon as I finish the question, if you just want to note it down, don't waste time by noting it down. Just take a screenshot so that you can refer it later. Taking a screenshot will save you time. So efficiency is what? Efficiency is the ratio of output power to input power, right? Right. Siddiqui Mullah, have you asked about break? Yes, we'll be having a break later, not now exactly. I'll be informing you whenever we get a break. So see, efficiency at 0.8 power factor lag. This you have to find out. Efficiency is generally output power by input power multiplied by 100. So you can write this in this manner, right? It is output power by output power plus losses. Input power, see, input power plus losses will input power minus losses will be is equal to output power. Therefore, input power you can write it as output power plus losses. Losses, right? So this multiplied by 100 you will get percentage efficiency. So what is output power? The rating of the transformer is given. Let us say S is the rating of the transformer. Then output power will be is equal to S cos phi. S cos phi. Right. So output at an xth fraction of load is x multiplied by S cos phi. X is a fraction of load. At a particular fraction of load, the output will be x multiplied by S cos phi. Again, this divided by x into S cos phi, output upon output plus losses. What are the losses? Copper losses, I square R equivalent plus iron losses. Let us call it as Wi. This multiplied by 100. So this is the formula you have to find out efficiency at any particular load, right? If it is full load, x will be is equal to 1. X will be is equal to 1 for full load. X will be is equal to 0.5, right, for half load. Half load. X will be is equal to 3 by 4 for 3/4 load. 3/4 load, or else you can say 3/4 of full load. Right. This way, X value varies depending on the load, right? X is nothing but fraction of load. Yes. So, see, if load is decreasing, the voltage is being constant. Voltage is being constant, but what is happening to copper loss? What is happening to the current? Current is decreasing. See, S is nothing but V into I. Voltage is constant, current is decreasing. Voltage is constant and the current is decreasing, right? Half load means current is half. Full load means current is IFL, right? If it is 1/4 load, current is 1 by 4th, right? Therefore, IFL into X, this will be is equal to I. I will be is equal to what? IFL multiplied by X. Therefore, you can write this I as X into IFL whole square, that is X square into IFL square R equivalent. So at any particular load, this is how you can find out the efficiency, right? Output power by output power plus copper losses plus core losses, right? Copper losses plus core losses, right? So the output power, the efficiency is asked at efficiency at 0.8 power factor lag, right? Full load 0.8 power factor lag. Full load means X is equal to 1. 0.8 power factor lag means cos phi is equal to 0.8, right? So you should use efficiency is equal to 1 multiplied by 300 kVA. 300 kVA is the rating of the transformer that is provided in the question, and cos phi is 0.8 divided by, this is 1 again, 300k, 300,000 multiplied by 0.8 plus x square, 1 square is 1, multiplied by full load current. See, full load current is given to be how much? In the question, they have mentioned what is the actual full load current. Or else if the full load current is not mentioned, you have to find out the full load current, right? The full load current, see, the voltage ratings of the transformer are given like this. It is a 300 kVA transformer and the voltage ratings are 11 kV by 400 volts. Is it 400 volts? Yes, 11 kV by 400 volts. 11 kV on the HV side and 400 volts on the LV side. So from this you have to find out rated current on each winding, right? So rated current on each winding, how will you get? S is equal to V into I is equal to S divided by V. Therefore rated currents on each winding is 300,000 divided by 11,000 slash 300,000 divided by 400, right? You will get the rated values of current, right? Ram Srivastava, just see here. See, I have to find out the rated current. Rated current is nothing but I is equal to S divided by V. That's it, right? So S is given to be 300 kVA. S is given to be 300 kVA, and you have to find out the value of this particular rated current, because the copper losses that are given in the test, they are not the full load copper losses. You have to find out full load copper losses. That is the twist in this particular question. See, the copper losses given in the test data are copper losses at 15 amperes. At 15 amperes, you got a copper loss of 2574 watts. 2574 watts, right? But as the current changes, the copper losses will change. What is the full load current? Just solve this and tell me what are the current ratings. 27.2727. You can write it as 27.27 bar. You can write it as 27.27 bar slash, on the 400 volt side it is 750 amperes. So 27.27 bar, these many amperes on the HV side and 750 amperes on the LV side, right? So now you have to find out the efficiency corresponding to the full load current. The current supplied through the HV winding was previously 15 amperes. Now you have to find out the copper losses corresponding to full load current, right? See, what are the copper losses actually? Copper losses I square R equivalent, right? Therefore, R equivalent is equal to WCU. Let us call copper losses WCU. R equivalent is equal to WCU divided by I square, right? So full load copper losses will be is equal to IFL square R equivalent. So it is WCU divided by I square multiplied by IFL square, right? So the copper loss is given to you, as there is no space here. I'm just erasing this, and I'll calculate the value of full load copper loss here, right? So WCU is 2574. This multiplied by IFL. Full load current is how much? 27.27 bar whole square. See, full load current squared divided by I square, 15 square. This is copper loss at full load, WCU FL, right? Full load copper loss. The full load copper loss is given by WCU FL, and calculate and tell me its value. What is the value of WCU? Which side should we choose here for full load losses? See, Srirama, it is given in the question already. It is given in the question that this particular short circuit test is performed on HV side, which means LV is short circuited, which means HV current you have to take, right? This 15 amperes current is flowing through the HV side winding, and 27.27, this is the HV side current. Got my point, right? The value of full load copper loss, tell me the value. Just tell me the value of full load copper loss. Yes, Lakshmi Narasimhan, very good. 8509. 8509.3 watts. This is the full load copper loss. Therefore, efficiency will be is equal to 300,000 divided by 300,000 multiplied by 0.8 divided by 300 multiplied by 0.8 plus 8509 into 3 plus the iron losses. Iron losses are quite clear from the, yes, Iron losses are quite clear. The iron losses are what? Iron losses are is equal to 5 to 5000 watts. The iron losses at rated condition are given to be 5000 watts. See, 400 volts is the rated voltage and 50 hertz supply is the rated supply, right? 50 hertz frequency is the rated frequency. Therefore, at rated conditions, the iron loss is 5000 watts, right? So once you get all the values, just calculate this. Efficiency will be is equal to how much percent? Just calculate and tell me the value. What is the value you are getting? That is 94 point something, right? So just calculate and tell me the value. 94.67 percentage efficiency is equal to 94.67%. This is the efficiency. See, from this question, what you can learn is, see, you can calculate efficiency at any particular load, any particular power factor, right? So provided you know the value of R equivalent. So if short circuit test data and open circuit test data are given, right, you know the value of R equivalent as well as you know the value of this, the iron losses at any particular iron losses at rated condition, right? See, if copper loss at any particular current is provided, see, copper loss at 15 amperes is provided. This current is other than the rated current, right? So if a current other than rated current is provided, then you have to find out the full load copper losses. आपको full load copper losses find out करना है. Once you find out full load copper losses, you will get efficiency. Efficiency is equal to 94.67%. Right? This way you can calculate the efficiency at any particular load by manipulating X, and at any particular power factor by manipulating cos phi. Right? The transformer's efficiency at any particular load and power factor can be calculated. So let us go through the next question. The next question is hysteresis and eddy current losses at 416 volts and 52 hertz are. Can anyone tell me what is the approach that we should use to solve this particular question? 416 volts and 52 hertz are. The hysteresis and eddy current losses at 416 volts and 52 hertz. Yes, V by F is provided to be constant. Yes, very good. First, we have to check whether Bm is constant or not. If Bm is not constant, we cannot find out. Right? So, until and unless you note that the flux density is not constant, flux density is constant, you cannot proceed. Right? So, if you know the flux density is constant, that is, flux is constant, once you know the flux is constant, that is, V by F is constant, right? You can proceed with the question. So after finding out the flux is constant, what you will do? Just tell me the approach. After finding out that the flux is constant, what is the approach that you are going to use? It is very good that you have found out V by F is constant, right? So what will you do? If B is constant, then hysteresis loss is directly proportional to frequency or eddy. Yes, yes, very good, Malesh. Sorry, not Malesh, it is Mahesh, right? Very good, Mahesh. The approach is correct. See, all of you know that the formula for hysteresis losses, WH, is equal to some hysteresis constant KH multiplied by B max power 1.6. This is eta generally. The iron core which we use generally in transformers. For that, the value of Steinmetz constant eta is 1.6 only, right? Multiplied by F, watts per meter cube. The unit for this is watts per meter cube. If the volume is more, obviously the hysteresis losses will be more, right? It is these many watts per meter cube. And eddy current losses is equal to Ke multiplied by B max whole square into F square watts per meter cube. You might be thinking about T square, thickness square. See here the thickness of the lamination. Once you have cut the core into slices, right? Once you have sliced the core, right? You have cut it into laminations, right? The thickness of laminations is a constant. I'm just including that thickness square, T square in Ke only, right? Therefore, you can say if B max is constant, see if B max is constant, if at all B max is constant, what happens is hysteresis loss WH will be is equal to WH will be is equal to some K suffix capital H. Let us say it is K suffix capital H. I'm including this B max multiplied by KH, and I'm multiplying both of them and I'm considering it as KH. It is some KH into F watts per meter cube, and eddy current loss is equal to some K suffix capital E multiplied by F square watts per meter cube, right? Only if V by F is constant, see V by F is equal to constant, then B max will be constant, right? So see whether V by F is maintained constant or not. In the open circuit test data given to you, it is the test is performed at two different voltages and two different frequencies. What are the different voltages? One is at 400 volts and 50 hertz, 400 by 50, right? The other one is 200 by 25, right? Both are constant. This is 8, right? Constant. 400 by 50 is equal to 200 by 25. And at what particular value did they ask to find out the losses? What particular value of voltage and frequency? It is 416 and 52 hertz, 416 volts and 52 hertz. This is also same as the above, right? So throughout all the tests, the value of V by F is maintained constant, which means B max is maintained constant, the flux is maintained constant. If flux is constant, then hysteresis loss is directly proportional to frequency and eddy current loss is directly proportional to frequency square, right? The total iron loss Wi is equal to hysteresis loss plus eddy current loss. Total iron loss is hysteresis loss plus eddy current loss. See, Wi is equal to hysteresis loss Kh into F plus Ke into F square, right? So from this, take F to be common. The frequency, you just take it common out of this RHS and divide iron loss with frequency. Wi by F is equal to Kh plus Ke into F, right? So this is again looking like a straight line, yes or no? This is Y is equal to mx plus c. Y is equal to mx plus c, right? If you plot this as a straight line, if you just plot its graph, Wi upon F and F versus F, right? So you will get some straight line like this. This y-intercept is nothing but kh, and the slope of this straight line, slope of this particular straight line is going to be is equal to ke, right? So you have to find out the value of ke and kh, right? So for that you have been given two data points on this particular straight line, right? At 400 volts 50 hertz, right, which means at 50 hertz the iron losses are provided, and at 25 hertz the iron losses are provided to you, right? So you have to solve these two equations and find out kh and the value of ke. Iron loss is constant loss and copper loss is variable loss. Right? Yes, Mahesh. Iron loss is constant and copper loss is variable loss. See, that is constant if voltage and frequency are maintained constant. If voltage and frequency are disturbed, iron losses will be disturbed. Under rated conditions, they are constant. See, why are they called as constant losses? Can anyone tell me why iron losses are called as constant losses? And why copper losses are called as variable losses? Just answer my question. Why iron losses are called as constant losses and why iron losses are called as, sorry, copper losses are called as variable losses and iron losses are called as constant losses. Why? What is the reason? Can anyone tell me the reason? No, Lakshmi Narasimhan. See, copper losses, copper losses are I square R losses. What is this I? I is load current. Load current, right? If load current is varied, if you just vary this load current is always variable, right? So if you vary this load current, what happens to copper losses? Copper losses will also vary, right? This arrow mark I'm just putting here to indicate variation, right? So copper losses are variable with respect to load current, whereas irrespective of load current, the iron losses are same, right? They do not depend on load current. Iron losses are, that is the reason why they are called as constant losses. They do not depend on load current at all, right? Because copper losses depend on load current. Very good, Mahesh. And Nagasrikar as frequency constant, iron loss are constant. Very good, very good. Right. Sri Rama is asking something at normal operating. Yes, construction is done. Iron losses doesn't vary. Very good. Very good, everyone. So you have to solve two equations. Iron loss at 50 hertz, 500 watts is the iron loss, and this is at 50 hertz is equal to KH plus KE into 50. This is equation number one. Let us say this is equation number one. And iron losses at another load are also given. That is 2000 watts. Iron losses at other load are 2000 watts. Other frequency, that is at 25 hertz, the iron losses are 2000 watts. And KH plus KE into 25. This is equation number 2, right? Solve the equation 1 and 2 and tell me the values of KH and KE. Just solve the equations 1 and 2 and tell me the value of KH and KE. Can the value of current in the armature circuit be same as before without addition of armature resistance as you have done in the previous question? No, without adding any external armature resistance, the armature current cannot be same, right? If you vary the load, if you vary the speed, or else if you vary the torque, armature current will vary accordingly. So if you add only external resistance, only then it is going to be the same as the previous one. So all of you have solved KH and KE, the values of KH and KE. What are the values of KH and KE? Yes, 60 and 0.8. Very good. KH is equal to 60. Hysteresis loss constant KH is equal to 60, and KE, eddy current loss constant, is 0.8. Right. So now what is asked? The iron loss at a frequency of 52 hertz, 416 volts and 52 hertz. Right. So put F is equal to 52 in this particular equation. You can write Wi is equal to KH into F plus KE into F square. that is equal to KH 60, 60 into 50, sorry, this is 52, 60 into 52 plus KE 0.8 into 52 square. Therefore, the iron losses you're going to get, the value of iron losses you're going to get in this part after solving this is 5283, 5283.2 watts. 5283.2 watts. These are the iron losses, right? So like this, you can calculate the iron loss any particular frequency when it is asked, right? So once VWAF ratio is maintained constant, the iron loss at any particular frequency can be obtained just by getting the values of KH and KE, just by solving the equations and getting the values of KH and KE, right? In this particular question, we have covered the voltage regulation of a transformer, which means equivalent circuit, knowledge of equivalent circuit should also be necessary, and the efficiency, calculation of efficiency at any particular load and power factor, and also the calculation of these iron losses individually, the value of eddy current loss and hysteresis loss at any particular frequency. Remember, this question is always asked for 2 marks in gate. This is repeated a lot. They repeat this a lot and they always ask this for 2 marks. Always this particular question is asked for 2 marks. So just remember, this is very important model. If you cover this, there is a probability that this question might appear in your gate 2020 exam, right? You will be getting 2 marks very easily. So let us take a small bio break for 8 minutes, which means just uh, have some water and come back, right? We'll take a break for 8 minutes. Sharply 8 minutes. Come back by 8 minutes. Yes, it will be audible now. So just give me the approach to solve this particular question. Just give me the approach to solve this particular question, right? So in this question, there are two three-phase transformers. There were two three-phase transformers, and both those transformers, right, uh, are connected to a particular load, a star connected load, right? So the line to neutral terminal of the star connected load is connected to the X plates of CRO in one at one particular transformer, and the line to neutral and the line to neutral voltage of the second, that is the line to neutral terminals of the second load, are connected to the Y plates of CRO. You can hear me now, right? So you have to look at the phasor grouping of the transformers. There are several questions. You should be able to obtain the phasor grouping of the transformers, and along with the phasor grouping, you have to obtain the phase difference between line to neutral voltages as well, right? Line to neutral voltages as well. So the question is not yet over. The questions are like this: the phasor group of first transformer, that is phasor group of transformer T1, is asked, and phasor group of the second transformer T2, is also asked. And if the line to neutral voltages are connected to X and Y plates of CRO, right? See, whenever there is a phase difference, two sinusoidal quantities which are having a phase difference, if they are connected to a CRO in XY mode, that will display a Lysage's pattern. All of you are familiar with this or not? If you are familiar, just give me the formula to calculate the phase in a Lissage, from a Lysage's pattern. Can all of you give me the formula to calculate the phase difference between signal fed to the X as well as signal fed to Y from a Lysage's pattern? Lysage's pattern से phase as well as phase difference निकालने का तरीका बताइए, formula बताइए. Just give me the formula, that's it. So if you look at the terminals, see A1, A2, this is A2, this is A1, this is B2, this is B1, C2, C1. A phase winding, B phase winding, C phase winding. If they are indicated in capital letters, they belong to HV side, right? So if these are indicated in small letters, A1, A2, B1, B2, C1, C2, you should be well versed with the nomenclature as well. If you do not know the nomenclature, you cannot answer the question, right? So A1, A2, B1, B2, C1, C2, these are small letters, which means they belong to LV side. This is LV side, this is low voltage side, and this is high voltage side, right? Again here, A2, A1, B2, B1, C2, C1, A2, A1, yes, B2, B1, C2, C1. These three are shorted, and this terminal is called as neutral. This is called as neutral. Neutral of LV should be indicated with small n, right? Neutral of LV should be indicated with small n. Whereas on the other hand, you do not have, on this side, on this particular winding, you do not have any neutral. In a delta winding, you don't have any neutral, right? You will not have any neutral in a delta winding. See, the questions from this section, that is three-phase transformers, are also quite frequent. Majority of the times they asked the questions on three-phase transformers for 2 marks only, right? Which means they have a good weightage. They have a very good weightage. So just for saving some space, I'm not just connecting the loads here. So just see the delta winding, delta connection here. A2 is connected to B1, B2 is connected to C1, and C2 is connected to A1, right? So to obtain phasor grouping of transformers, you should obtain the phasors on LV side as well as HV side, right? All the three phasors on LV side as well as HV side, right? So the phasor, there are certain conventions that which you need to be followed, generally followed in manufacturing of three-phase transformers. The conventions are phase sequence is positive, right? For obtaining the phasor group or phasor group from the connection diagram, or else to obtain the connection diagram from the phasor group, right? The phase sequence should be positive, ABC, which means the peak in voltage VA comes first, next the peak in voltage VB comes next, and peak in voltage VC comes later, right? So all the three have a phase difference of 120 degrees. All the three phasors have a phase difference of 120 degrees, and one A comes first, B comes next, and C comes the third, right? So this is positive phase sequence. Generally, positive phase sequence is assumed, right? If it is BAC, this is negative phase sequence, right? B is coming first, A is coming next, and C after A, right? This is negative phase sequence. So we do not use negative phase sequence. We do not assume negative phase sequence. To find out the phasor group of this particular transformer, you have to assume positive phase sequence. And the terminals, see, bubbled terminals means these terminals are given supply, or else from these terminals we have taken the line voltages, right? Bubbled terminals will give you line voltages, or else you give supply to these windings from the bubbled terminals, right? So these indicate the line terminals, or else you can say supply terminals, right? Line terminals or supply terminals. And see, the phase A in HV side, that is phase voltage in HV side, will be in phase with phase voltage in LV side, right? So LV side, this phase voltage between A1 and A2, this will be in phase with A1 A2, right? See, either they will be in phase, or else either they will be at a phase of 180 degrees. Either they will be parallel or they will be anti-parallel, right? See, parallel means this is A2 A1 V suffix A. From A, just rotate by 120 degrees, you will get V suffix B, right? This is B2, this one is B1. From B, just rotate 120 degrees, you will get the C phasor, VC. This is C2 and this is C1, right? See, positive phase sequence means from VA you rotate by 120 degrees, you will get VB. From VB you rotate by 120 degrees, you will get VC. From VC you rotate by 120 degrees, you will get VA again, right? 120 degrees in clockwise sense, right? See, this is star connection. A1, B1, C1 are connected, and neutral is obtained from A1, B1, C1. Therefore, A1, B1, C1 are connected, right? So this common point is indicating what? This is indicating neutral, right? Similarly, this is also a star connection, right? This is also going to have the same thing, right? VA phasor, VB phasor, and VC phasor. This is VA, VB, VC, right? So from A2 you are taking the supply, or else to A2 you are feeding the supply, right? The terminal, the bubbled terminal is A2. Therefore A2 should have an arrow mark here. मतलब arrow head जो है वो A2 पे रहेगा. Arrow head will be on A2 because you are giving supply from this bubble. You're giving supply voltage from this bubble, or else you're taking the supply from this particular terminal. From A2 you're taking the supply, which means A2 should be having an arrowhead. A2 should be having an arrowhead. B2 should be having an arrowhead, and C2 should be having the arrowhead, right? So all the bubbled terminals will have arrowheads, right? Here, see A2 arrowhead must be at small a2, arrowhead must be at small b2, arrowhead must be at small c2. Look at this. Here arrowhead must be at small a1, arrowhead must be at small b1, and arrowhead must be at small c1. This is where you get 6 o'clock configuration. See, this phasor will be anti-parallel. This phasor will be anti-parallel to the line to neutral phasor here, right? That is the reason why this is called as 6 o'clock configuration. See here, a1 a2. See, how can we say that this is 6 o'clock? Let us say you have a voltage source. This is your voltage source. You have taken positive here and negative here. This is Vm sine omega t, right? This is the voltage source, and you have connected positive of the load. This is your load, let us say. Positive of the load is connected to positive terminal, negative of the load is connected to negative terminal, right? You will observe a voltage like this. If you want a voltage which is exactly anti-parallel to this, what you will do is you connect the positive to negative terminal, negative to positive terminal, right? So you will get a voltage like this, which means there is 180 degrees of phase difference between each of them, right? 180 degrees of phase difference between each of them. See here, VA1, A2. This is VA1, this is VA2. VA1, A2 here is at 90 degrees, let us say, right? What about VA1, A2? This A1, A2, that will be like this. Here, arrowhead will be at small a1 and arrow tail will be at small a2, right? So you got to know how this 180 degrees of phase difference is there, right? See, this and this, both of them have 180 degrees of phase difference. You look at the phase difference, this and this have 180 degrees of phase difference. They are completely anti-parallel, right? Everyone is getting it? Yes or no? This is at 90 degrees, this is at minus 90 degrees, right? They have a phase difference of 180 degrees. Similarly, see here, rotate 120 degrees from phase A, right? Rotate by 120 degrees from phase A, you're going to get the phase B. Both are fed from a common supply, which means both the phasors on the supply side will be same, right? So see here, this is B1, sorry, this is B1 and this is B2, right? Rotate by 120 degrees from phase B, you will get phase C, C1, C2, right? Just acknowledge in the chat box. All of you got it till here or not? Any doubts still here? Just acknowledge in the chat box. And here you will get neutral in the LV side, neutral on the HV side. Got this or not? Any doubts till now? Any doubts? But for delta connection, it should take triangle. Yes, yes, Lakshmi Narsimhan. See, Both of these are star connections. We did not yet form the phasor group for delta, right? So everybody got till now. It is clear, right? So see here, A2 is connected to B1. A2 is connected to B1. See, from A2 you are taking supply, which means arrowhead should be towards A2, right? And A1 and A2, this phasor will be parallel, right? Parallel means this is the phasor. This is A2, this is A1, this is V small a, right? On the delta side, this is V small a, right? So A2 is connected to what? A2 is connected to B1, right? So from A phasor, just rotate the phasor by 120 degrees, you will get B phasor. Rotate by 120 degrees, you will get B phasor, right? So angle of B phasor should be like this, but B phasor is connected to A2, not A1. B1 is connected to the tail of B phasor is connected to A2. Tail of B phasor is connected to A2. Therefore, this is B2, this is B1, right? Again, see, you can check this in this way. See, just extend this A, and the angle between this A's extension and B is how much? 120 degrees. So A phasor rotated by 120 degrees, you will get B phasor, right? The only thing is this tail is connected to A2. Tail of B phasor is connected to A2. Next, tail of C phasor is connected to B2, which means, see, extend B phasor, and from B phasor you just rotate by 120 degrees. This is B phasor. If you rotate by 120 degrees from B phasor, you will get C phasor like this. So C phasor will be joining B2 and A1. This is C2, this is C1, right? So from C you have rotated by 120 degrees and you got, from B you have rotated by 120 degrees and you have got C phasor, right? So even if you rotate by 120 degrees from C phasor, you will get A phasor, right? This should always be followed. See, if at all this phase sequence is not followed, you're doing something wrong. यहाँ गलत कर रहे हो आप, right? So while calculating, while obtaining the phasor groups, you should always be alert that phase sequence is always followed. What phase sequence? Positive phase sequence. After A phasor, B phasor should come. After B phasor, C phasor should come, right? So this should be the phase sequence. See, if supply is given to A2, whereas supply is collected from A1, which means A1 has an arrow here. Arrowhead will be towards A1. Both the voltages will be in same phase. The reason why I am saying that both the voltages will be in same phase is, see, let me just erase this. I'm just erasing this primary side. The reason why I'm saying this is, how is a three-phase transformer constructed? See, a three-leg three-phase transformer. Let us say you have a three-leg three-phase transformer. This transformer has three core limbs, right? On the first core limb, you will have HV as well as LV of phase A. On the second core limb, you will have HV as well as LV of phase B. On the third core limb, you will have HV as well as LV of phase C, right? See, fluxes are common. For phase A, flux is this phi A, right? So as soon as the flux is common, what is E? E is equal to N d phi by dt, right? Flux is common to both the windings HV and LV, which means both the voltages should be in same phase. To obtain opposite phase of 180 degrees, what you have to do is you have to invert the terminals, right? You can, in each phase winding, you can obtain either 12 o'clock configuration or 6 o'clock configuration. 12 o'clock means the LV phasor is towards 12 o'clock position in a dial, in a clock, and the HV phasor is towards 6. This is 12. Sorry, the HV is also towards 12. LV and HV both are towards 12. Right? 6 o'clock position means this is 12 and this is 6. Right? 6 o'clock position means LV is towards 12 and HV is towards, sorry, LV is towards 6 and HV is towards 12. This is 6 o'clock position, right? In a single phase winding, you can obtain either 12 o'clock or 6 o'clock position. Whereas from star to delta and delta to star, you can obtain many other positions also, right? That is 1 o'clock, 1 o'clock, 11 o'clock, 5 o'clock, 7 o'clock, etc. You can obtain many other positions as well, right? Clear till now? Right, the voltages will be in phase. The reason for that is the core limbs are common for each and every winding, each and every phase, right? So now look at this. You can obtain an arbitrary neutral on the delta side, right? You cannot have a neutral on the delta side. Can anyone tell me where should I place the neutral on delta side? If I'm assuming an arbitrary neutral, where should I place the neutral on neutral terminal on delta side? Neutral point, the neutral point should be at, tell me, someone tell me where should I place the neutral point? Yes, A1, very good. A1, Lakshmi Narasimhan? No, not at all. See, A1 and C2, how are they neutral? See, at this, just look at this. This is a triangle. This is a triangle, right? So these are the line to line voltages. If I join these two voltages, that is a line to line voltage. If I join these two voltages, that is a line to line voltage. So at the center of this particular triangle, I have neutral. Similarly here, at the center of this particular triangle, I have neutral. So tell me where should be the neutral? Yes, very good. Very good, Sri Rama. The neutral should be at the center, which means you can say centroid of the triangle. At the centroid of the triangle, there should be the neutral phase, neutral terminal, right? So physically, you cannot obtain neutral in a delta winding. In a delta winding, see, where can you get a neutral terminal? You cannot obtain, you cannot connect neutral terminal anywhere, right? Whereas in the phasor, if you want to represent, you can represent the neutral terminal at the centroid, right? So let us look at the phasor groups. See, the line to neutral phasor, the line to neutral phasor in the LV side will be connecting A2 to N. Yes or no? This is the line to neutral phasor in the LV side. Whereas the line to neutral phasor in the HV side, यहाँ थोड़ा clumsy हो गया. I'm just writing it here. The line to neutral phasor here. See, this is A line and this is neutral, right? V line to neutral in HV side, right? So whereas this is A line, see A2, A2 is giving you A line of phase A. This is A2, right? So connect neutral and A2. This is the line to neutral phasor. Line to neutral phasor here, right? On the LV side, this is V line to neutral on LV side. V line to neutral on LV side. Now tell me what is the phase difference between the line to neutral phasor on HV side and line to neutral phasor on LV side? Can anyone tell me? What is the phase difference between line to neutral phasor on HV side and line to neutral phasor on LV side for the transformer 1? For transformer 1. Is every one of you familiar with three-phase transformers or not? Three-phase transformers are very important in gate point of view. See, if you neglect this phasors, right, phasor groupings, you will end up leaving a 2 marks question, right? Many a times, based on phase difference, you will be getting a 2 marks question. A similar kind of question also came in gate. Similar question. The question which we have framed is easier. The question which gate has given is, sorry, the question which we have framed here is tougher, and the question which is framed by gate is a little easier, but still we have similar questions in gate, so it is important. Very good, Anjali Kumari and Lakshmi Narasimhan. It is 30 degrees. See here, neutral to line, neutral to line here is on the HV side is like this, completely erect, and neutral to line on the LV side. On the LV side, see, I'm drawing the LV side triangle here. LV side triangle. The triangle on the LV side is something like this, right? This is A2, this is A1. Therefore, this is neutral. So join line and neutral. So there is 30 degrees of phase difference between both of them. 30 degrees. Right. So the LV side line to neutral phasor is at 11 o'clock position, and HV side line to neutral phasor is at 12 o'clock position. Right. LV side line to neutral phasor is at 11 o'clock position, and HV side line to neutral phasor is at 12 o'clock position. Tell me, what is the phasor group? HV is this and LV is this. What is the phasor group? LV side, LV side is, C, is at 11 o'clock position, and HV side is at 12. Right, HV phasor is at 12. So which clock is this indicating? Give me the answer. Which clock is this indicating? Which clock does this indicate? This indicates 11 o'clock. Very good, Lakshmi Narasimhan. It is YD11. See, the HV side is delta star connected, LV side is delta connected, right? HV side is star connected means HV side you will represent by capital letter, right? The nomenclature, you must be knowing the nomenclature. HV side should be written by capital letter. LV side is indicating delta connection, which means LV should be written with a small letter, HV star, LV delta, and the phase difference is like this. This is indicating 11 o'clock position, which means YD11 is the phasor group. The phasor group is YD11. Should we always take HV at 12 o'clock? Yes. Srirama, I'll tell you the reason. See, I was about to tell the reason at the last, but as you have asked, I'll tell you the reason. See here. See, this 11 o'clock can be written like this also. This is the clock, right? So 11 o'clock, just assume with this, it is at 11 and 12 positions like this, right? So we can rotate this wherever we want. We can rotate this like this also. See, if we have rotated this by 90 degrees in this manner, it will be 9 here and it will be 8 here. The HV phasor will be like this and LV phasor will be like this. This is LV, this is HV. You can call it as 845. 845. Right? See, you can call it as 845, but why to increase complications? You can simply represent it with 11, right? You can say, See, I am representing it as 8:45. Someone is representing it as 11, and someone else is representing it as some 4:15. Right? All these are possible for same configuration. The difference is to indicate phase difference of 30. We can use the simplest notation. Right? So if we bring the HV side phasor to the 12 o'clock side, we can give the representation in a simplest manner. That's it. Only that is the reason. Nothing else. Right? So always wherever you get the HV side phasor, just rotate the HV side phasor to 12 o'clock position so that the notation is simplest and universal notation. This is the universal notation. Right? So instead of writing it as 8:45 or 4:15, you can use the simplest notation, that is 11 o'clock. Right? Yes, very good. Mahesh, LV side leads the HV side. LV side line to neutral phasor. LV side line to neutral phasor leads the HV side by 30 degrees. That is YD11. Exactly. So you got the phasor group of transformer T1. Phasor group of transformer T1 is YD11. What about the phasor group of transformer T2? Can you tell me the phasor group of transformer T2? It is quite evident from this particular diagram. डायग्राम में साफ दिख रहा है. It is directly visible. Right? What is the phasor group of transformer T2? Transformer T2. Yes, YY6. Very good. See, HV side was Y connected. LV side is also Y connected. Right? It is YY. But if you look at the line to neutral phasors, see, the LV phasor it is at 6 o'clock position and HV phasor is at 12 o'clock position. LV is at 6 o'clock position and HV is at 12 o'clock position. 12. HV is pointing towards 12 and LV is pointing towards 6, which means ये 6 बज चुका है. This is 6 o'clock. Right? So you can write this particular configuration, that is phasor group of transformer T2 is equal to Y connected on HV side, Y connected on LV side, and the phasor group is 6 o'clock. This is YY6. Therefore, the second question is also answered. That is phasor group of transformer T2 is, yes, exactly, Mahesh, very good. Right, there is exactly 180 degrees of phase difference between LV and HV phasors. So now, the third question, just look at the third question. It is a little bit tricky. So no one have answered how to find out the phase difference. I've asked previously. What is how will you find out the phase difference when a Lysage's pattern is given? When a Lysage's pattern is given to you, what is the formula that you generally use to find out the phase difference? Phase difference between two phasor quantities. Right? What is the formula you generally use? To find out the phase difference between two quantities, what is the phasor? What is the formula you generally use? YY6 phase shifted. Yes, can anyone answer? What is the formula from the Lysage's pattern we should use to find out the phase? Some people call it as Lysage's pattern or Lysage's pattern. No matter. It doesn't matter. Right? So let us say the Lysage's pattern is somewhat like this. It is covering these two quadrants, first and third, and the Lysage's pattern is somewhat like this. Tell me the formula for each case. Right? Formula of phase difference in each case. No one remembered it. You did not remember or what? See, let us call it as x2. This I'm calling it as x1. I'm calling this as y2 and this as y1. Right? x2, x1, y2, y1. The phase difference between quantity applied to x plates as well as the phase and the quantity applied to y phase. The phase difference is given by phi is equal to sine inverse of x2 by x1 or sine inverse of y2 by y1. Sine inverse of x2 by x1 or sine inverse of y2 by y1. Very good, very good. Lakshmi Narasimhan, very good. Right? So if it is like this, if it is covering the second quadrant and the fourth quadrant, then phase difference phi is given by 180 degrees minus sine inverse of 180 degrees minus sine inverse of x2 by x1. This I'm calling as x2 and this I'm calling it as x1. This is y2. This is y1. Right? You can use this formula, or else you can use the ratio of y2 by y1 also. Right? You can use the ratio of y2 by y1 as well. Right? So it is given, the Lissajous pattern is given, and the ratio of x1 by x2 is asked. X1 by x2 is asked. So if you look at the Lissajous pattern, that resembles this. So which formula should you use? It is 180 minus sine inverse of x2 by x1. ये measurements का concept है. This belongs to measurements, but still we are just recalling it here, right? So multiple concepts can be used in a single question. Questions can be mixed, intermixed questions may come in your GATE exam. So phi is equal to 180 minus sine inverse of x2 by x1, right? So you should find out, you should give the value of x1 upon x2. So for that, you should have to find out the difference between the voltages applied to X plates and Y plates. So look at the question. Just look at the question. Just go through the question. So if you look at the windings, how are the windings connected? I'm just putting it on full screen. How are the windings connected? Between the terminal A2 and C2, right? The star connected load branch is connected. Between the terminals A2 and C2, star connected load branch is connected, which means, see, the line and neutral, the line and neutral of the line voltage VAC, right? VAC देखो एक बार, line voltage VAC जो है उसमें से line to neutral voltage obtain किया गया है. Line to neutral voltage has been obtained from the line to line voltage, right? How? By connecting a star network, balanced star network, right? So line to neutral voltage on the delta side is compared with line to neutral voltage on the star side. Line to neutral voltage on the delta side is compared with line to neutral voltage on the star side. So you have already seen the phase difference. Line to neutral voltage on the delta side. How is the line to neutral voltage on the delta side? It is subtending at an angle of 30 degrees with respect to the vertical. See, if this is the vertical, it is subtending an angle of 30 degrees with respect to vertical. This is 30 degrees. This is LV phasor of delta side, and the LV phasor of line to neutral, LV phasor of star side is this. This is exactly pointing towards 6. So if this is 30, what about this angle? Tell me two angles. The angle I'm indicating with phi 1 and this angle which I'm indicating with phi 2. What are the two angles? Phi 1 and phi 2, the values of phi 1 and phi 2. So how you got this from this particular diagrams? See, line to neutral phasor here and line to neutral phasor here. I just separated both of them and I've just put it here, right? And it is also mentioned in the question that all the neutrals are grounded, which means all the neutrals are at same position, which means the neutral of this as well as this phasor both are at same position, which means there is absolutely Lakshmi Narasimhan, very good. It is 150 degrees, right? The phase difference is 150 degrees, or else you can consider the same as minus 210 degrees also, minus 210 degrees, 180 degrees plus 30 degrees, right? Negative of 180 degrees plus 30 degrees, or else 150 degrees, right? You can consider either of them, any one of them, right? So phi is equal to 180 minus sine inverse of x2 by x1. This value phi is equal to how much? Phi is equal to 150 degrees. 150 degrees is equal to how much? 180 minus sine inverse of 180 minus sine inverse of x2 by x1, right? So sine inverse of x2 by x1 is equal to 30 degrees. That implies x2 by x1 is equal to 0.5. X2 by x1 is equal to 0.5. Is x2, if x2 by x1 is 0.5, then x1 by x2 will be is equal to 1 by 0.5, that is equal to 2. The value of the answer for this particular question is how much? 2, right? Why did we take the phasor of bottom case? See, Srirama, if you look at the load connection, I'm still showing it here in the question, right? The load connection is still shown in the question. Just look at it. See, the line to neutral phasor on the delta side is connected to CRO, as well as the line to neutral phasor on the star side is also connected to CRO, which means these are connected to Y plates, these are connected to Y plates, and these are connected to X plates, right? This particular voltage is connected to X plates, and this particular voltage is connected to Y plates, right? So between these two voltages, what is the phase difference? That is what we have obtained here. Between these two voltages, the phase difference is 150 degrees. So from that particular calculation, we have got x2 by x1 ratio. From x2 by x1 ratio, you can simply get x1 by x2 ratio. See, to solve three-phase transformers, knowledge of these phasor diagrams is very much important. Not only three-phase transformers. If you know phasor diagrams, you can easily understand machines. Electrical machines is very easy to understand graphically. If you go by graphical approaches, you can understand this subject as easy as possible, right? The easiest way to understand electrical machines properly is going by phasor diagram approach. So phasor diagrams are the fundamentals you should know in electrical engineering. In networks itself, you should be knowing about phasors, right? So if you learn phasors properly, you'll be applying phasors in electrical machines, right? Even in electrical measurements, how would you get those formulas of wattmeter, 2 wattmeter method and all, right? And you would get, you have the phasor diagrams of CT and PT as well, right? So everywhere in electrical engineering, you will be using phasors a lot. A lot means a lot, right? So get well versed with the phasors. That is very important. So this model of question in from three-phase transformers is very much important, as we get questions from this sector repeatedly. We get questions from this sector a lot, right? So let us look at the next one now. The next question is based on auto transformers. So just look at the question and tell me what is the approach that we should use to find out the answer. I'm just putting it to full screen. Just tell me the approach that we should use to find out the answer for this question, to arrive at the solution. So what is asked? The rating is given. Rating of the auto transformer is 20 kVA, and the voltage ratings are 100 volts by 200 volts. The maximum kVA rating should be, right, if it is a two winding transformer whose rating is 20 kVA as well as 100 volts by 200 volts, this is reconnected as an auto transformer to obtain maximum kVA. So what is the maximum kVA rating? That is the question. See, obtaining maximum kVA rating of auto transformer is an area in GATE where you get questions frequently, very frequently. So just, even if you by heart this method blindly, by heart this particular method of finding out the kVA rating of auto transformer blindly, you might be getting a simple question from this, right? You'll be getting a simple question from this even if you just by heart the method. So let us just look at the procedure now. Yes, Mahesh, we can make in two different configurations. That can be made in two different configurations. Just I'll be just showing you here. Right. See, two different configurations are possible. One is, it is, just note down the rating first. It is 20 kVA and the voltages are 100 volts by 200 volts. Right. So you can connect it this way. 100 volts winding. You can supply the 100 volts winding and you can obtain the supply across 100 volts plus 200 volts, right? See, if the dots are like this, dots are connected like this, if the dot configuration is this, see, you are supplying this transformer with this voltage source. See, this is positive. From positive, see, this transformer will act as a load to this particular thing, right? So it will always draw current, right? So current will be entering this positive terminal. If current enters the positive terminal, what happens to the positive terminal of the other winding, right? You will see a positive voltage induced here. If current enters the dotted terminal, if current enters the dotted terminal, the dotted terminal will have positive. Dotted terminal will induce positive. So across this, the voltage is 200 volts, right? This is one configuration possible. Turns ratio on should be maximum versus ticking. I didn't get you, Mahesh. If we make 100 by 300, then turns ratio is 3. So not possible. See, I'll discuss all the possibilities, Mahesh. Just see here. This is 100 volts and 200 volts. The output voltage is how much? 300 volts. This is one possible configuration, and you can obtain it this way also. 100 volts winding is fed and supply is taken across 200 volts winding in series with the 100 volts winding, but the dots are like this. Dot yahan par hai aur yahan par dusra dot, right? So if current enters this particular dot, see, 100 volts you are applying here. If current enters this particular dot like this, positive will be induced at the other dotted terminal, which means positive here, negative here, right? The voltage here is 100 volts, this voltage is 100 volts, this voltage is 200 volts. See, 100 volts and 200 volts are opposing each other. 100 volts and 200 volts, they are opposing each other, which means the resultant voltage is 100 volts like this, minus 100 volts. You can say the resultant voltage is this, minus 100 volts, right? This is the second possible configuration. And let us look at the next possible configuration. Next configuration is this. See, you may supply the 200 volts side. 200 volt side you may give supply. The 100 volt side plus 200 volts winding, you will add them in series and you might be obtaining the supply across this. So dot is here, let us say here and here. You are supplying 200 volts through the supply, right? So there is 200 volts here, and this is 100 volts. So you can see the polarities are opposite again, 200 volts, 100 volts. So you will get a positive 100 here, negative 100 here. This is the output voltage, 100 volts, 100 volts, right? So there is one more configuration possible. One more is you can supply the 200 volts again, and you may take supply from the 100 volt side, but now the dots are different. You have a dot here, you have one more dot here, right? So if you supply with 200 volts, current will enter the dot, positive, uh, current will run through the positive, right? If the current enters through the dot, positive will be induced across this. The voltage across this is positive, which means here it is 100 volts, and here also it is already the applied voltage will apply across this directly, that is 200 volts. 100 plus 200, what is the voltage again? It is 300 volts. So these many configurations are possible, right? You can get 300 volts at the output or else 100 volts at the output, and the polarities are different. Polarities, you can obtain different polarities, right? So these many configurations are possible. Maximum KVA rating is 60 KVA. Very good, Mahesh. See, actually you will have formulas to find out KVA rating. KVA rating of auto transformer, to find out the KVA rating of auto transformer, you will have formulas. But I'm going to tell you an approach, a special approach, using which you need not use any formula, because the reason is, see, you will have 4 different formulas for different configuration. If you go by that particular formula, it is, I'm 100% sure that majority of you are going to forget that particular formula. You won't be able to remember that formula, right? To find out the rating of any transformer, how is the rating of any transformer fixed? See, voltage rating multiplied by current rating, you will get the rating of the transformer. See, it is given as 20 kVA. How is it 20 kVA? This S is equal to 20 kVA. This is equivalent to what? V into I. This S is nothing but V into I, right? So if I just multiply the current with voltage, I'm getting the ratio kVA rating of that particular two winding transformer. So what are the current ratings? 100 volts by 200 volts is the voltage rating. The current rating is like this. See, 200 kVA divided by 100. 20 kVA divided by 100 upon 20 kVA divided by 200, right? So these many amperes are the current ratings of each and every winding. Current rating of LV winding is how much? 20,000 divided by 100, it is 200 amperes. 200 amperes slash 100 amperes. These are the current ratings, right? Rating of LV winding is 200 amperes. Rating of HV winding, current rating of HV winding is 100 amperes. So out of all these configurations, find out the rating of each and every configuration. See here, if you connect a load across this, let us assume you have connected a load across this, right? So, and you have fully loaded the transformer. Fully, how much load you can apply on the transformer? Which winding is this? This is HV winding. HV winding current rating is how much? HV winding current rating is 100 amperes. So you can draw a maximum of 100 amperes through this winding, not more than that. So if you draw more than 100 amperes through this winding is going to die. ये क्या हो जाएगा? एक पॉपकॉर्न बन जाएगा, मतलब जल जाएगा winding will burn out, right? So you can draw not more than 100 amperes from this particular winding, not more than 100 amperes. Therefore the rating of this particular configuration is 300 multiplied by 100. 300 multiplied by 100, how much is it? That is 30 kVA. Rating of this configuration is 30 kVA. Rating of the second configuration. Just look at this rating of the second configuration. The output voltage is 100 volts, right? If you connect an external load, you can drive a current of maximum. See, I, the current is flowing in this manner. The current is flowing in this manner, right? How much current can be flown through this HV winding? A current of 100 amperes at maximum. 100 amperes at maximum can be flown through this particular HV winding. Therefore, the rating of this particular configuration is 100 volts multiplied by 100 amperes. Rating of this configuration is 10 kVA. 10 kVA. Similarly, rating of this configuration 100 volts multiplied by how much current this LV winding can carry. This LV winding can carry a current of 200 amperes, right? This can carry a maximum current of 200 amperes. Therefore, 100 multiplied by 200, the rating of this configuration is 20 kVA again. The rating of this particular configuration is 20 kVA, right? So look at this configuration then. 100, this 100 volts winding can carry how much? This 100 volts winding can carry 200 amperes of current. The rating is 300 multiplied by 200. It is how much? It is 60 kVA. So out of all these configurations, which is giving you maximum kVA? This particular configuration, right? You need not analyze all these things. I'll give you a shortcut, right? So then cannot take rated current through kVA, only take rated current through load. No, I rated is equal to 200 amperes and I rated is equal to 100 amperes. Mahesh, Mahesh, I didn't get your doubt exactly. So see here, there are 4 different configurations. Which configuration is giving you maximum kVA? See, kVA S is nothing but product of voltage and current, right? Product of voltage and current. KVA is maximum when voltage is maximum and current is maximum. When you can draw maximum current from the load and when you can maximize the voltage across the load, right? The KVA will be maximum. Or else you can say you can invert the configuration also. You can give a supply of 300 volts and you can take supply from here also, right? Invert this, that is also possible, right? So see here, out of all these configurations, this configuration is giving you maximum kVA. How is it giving maximum kVA? It has added 200 volts to 100 volts, 200 volts with 100 volts. The resultant voltage is 300 volts. You should obtain maximum voltage and see maximum current out of primary and secondary, out of HV and LV, which can carry maximum current. LV can carry maximum current, right? Maximum rating of an auto transformer constructed from a two phase transformer, sorry, constructed from a two winding transformer is nothing but sum of LV and HV voltages, VHV plus VLV multiplied by ILV. That's it. Maximum voltage should be maximum and current should be maximum, right? So VHV plus VLV is 300, ILV is 200, 300 multiplied by 200. You would be getting how much? You would be getting 60 kVA. This is equal to 300 into 200. You need not memorize any formula. No formula is needed. See, always go by no formula approach. जितने कम फॉर्मूले को याद रखेंगे उतना बेहतर है, राइट? सो रिमेंबर एज लेस एज पॉसिबल, राइट? अगर आपके याद में मतलब ज्यादा याद रखेंगे तो फिर भूल जाएंगे एग्जाम में जाकर. यू विल एंड अप गिविंग रॉन्ग आंसर्स, राइट? सो यू शुड minimize the number of things you memorize. To get maximum KVA turns ratio should be minimum. It's short approach. No. uh, yeah, Mahesh, there are certain conditions that should be satisfied always, right? So if you go by studying all those four conditions, you will forget and you will end up giving a wrong answer. So I don't recommend that particular method. This is the simplest method. It is nothing but VHV plus VLV multiplied by ILV. See, provided that maximum KVA rating that is obtainable from a two winding transformer is asked, right? So many a times the configuration is given to you, and they will ask you to find out the KVA. Even that is simple. See, you will find out the voltage, what is the output voltage, and what is the maximum amount of current that you can draw from the winding associated with the load. The winding associated with the load here is HV, whereas here is the winding associated with the load is LV, right? So the current that can be drawn by this is 200 amperes. The current that can be drawn by this is drawn from this is 100 amperes. So depending on the winding and the voltage, right, you have to obtain the KVA rating. This is the simplest approach and easily understandable approach. So no need to remember any particular formula. Is it clear, everyone? Is it clear? Still any doubts in this? Is the approach clear completely? See, I'm here to convey you the smartest approaches, the best approaches, so that you can minimize the amount of time you consume in gate examination. And if you minimize the time you consume for each question, then you can pay more attention and more time towards the lengthy questions, or else you can say you can give more time to the other questions, right? So that you can attempt maximum and you can maximize your marks बढ़ जाएंगे आपके, right? So use always try to use the smartest approach. What is the full form of gate? Can anyone tell me what is the full form of gate? Full form of gate. What is the full form of gate? Graduate graduate aptitude test in engineering, right? Gate is a test on graduate aptitude test. Aptitude test in engineering, right? What do you mean by aptitude? Very good. What do you mean by aptitude? Aptitude means being apt. Apt means appropriate. अब जितना appropriate हो उतना बेहतर, right? Being apt, as apt as possible, right? So aptitude, graduates aptitude test in engineering. If you developed your aptitude, you are more appropriate. See, in the DC machines question, we have solved what is asked in the question using a simplest approach, right? So if we have solved using the first approach, which I've mentioned in the question itself, right, which I've mentioned in the solution, that is unnecessarily you're solving the other things R, A, E, B, which are not asked, right? This is not appropriate to solve unnecessary things. If you are able to approach at the direct solution, direct answer, that is the most appropriate approach, right? So go by the appropriate approach. Let us say there are two persons 1, P1 and P2, right? P1 has more aptitude, P2 has less aptitude, right? Aptitude means being appropriate, which means P1 is using more smart approaches, P2 is using less smart approaches. One who uses more smart approaches, one who uses smartest methods to solve the questions, he is said to have more aptitude, which means he will score more in gate, right? So aptitude applied to engineering, he will score more, P1 will score more, P2 will score less. So develop aptitude. To develop aptitude, you have to look for, you have to search for the smartest methods always, right? Always try to search for the smartest methods. So one thing I forgot to tell you, we are going to we are going to complete today's session till transformers only till transformers, and we are done with transformers, right? So after transformers we are left with induction motors and synchronous machines, induction machines and synchronous machines. These two, for covering these two sessions, we have these two topics, we have a separate session for tomorrow, right? So all of you follow up tomorrow's session, and we'll be starting with our doubt solving session today, right? So this is about today's session, and let us start doubt solving session. If you have any doubts, please get them cleared from now itself. From overall the entire electrical machine subject, if you have any doubts, get them clarified from me. So any doubts till now regarding the questions which we have solved? Do you have any doubts regarding the questions which we have solved? Are there any doubts? Do you have any questions from the do you have any doubts from the questions which you have solved till now? Any doubts in that? Are the questions completely clear? Yes, Lakshmi Narayan, I'll be dealing with compensating windings, of course. And any more doubts and interpoles? Yes, sure, sure, Lakshmi Narayan. Lakshmi Narayan. I'll be giving you uh, information in short regarding compensating windings and interpolar windings. Any more doubts? Remember my words. Read the question as clearly as you can, right? So always start using gate calculator from now itself. Abhi se chalu kar do gate calculator use karna, right? So start using gate calculator from now itself. Read the questions as much as question as clearly as you can, right? So concentrate on the question. Also, before going to the exam, just develop aptitude. Aptitude means smartness, right? So try to use as smart approaches as you can, right? You will get as much marks as you can, right? You can get maximum marks, right? Sai Tarun, tomorrow's timing, you can go through the timetable which is given to you. You will find a timetable in the description, right? Please go through the timetable. You will find tomorrow's timetable, tomorrow's timings and all. Yes, tomorrow only, Mahesh. Induction and synchronous motor questions, induction motor and synchronous machines classes will be tomorrow only, right? That session is tomorrow only. Yes, Lakshmi Narayan has asked a question uh, to clarify regarding compensating windings and interpolar windings. Let us see. See, what are compensating windings and interpolar windings? I'll tell you in short. See, compensating windings, the name itself indicates they are here to compensate armature reaction. Let us say this is a DC machine, right? This is a DC machine. So you will have north and south poles like this. The field poles like this, north and south, north and south field poles, right? So on the armature you will have conductors, armature conductors. These are the armature conductors you have. and let us say our machine is rotating in this particular direction with a speed omega, right? Let us say this is a generator and this is rotating in this particular direction. So a conductor is just below the north pole and it is rotating in this particular direction. What is the velocity, direction of velocity? Yes, Mahesh, please go on, ask your question. See, direction of velocity at any particular instant will be tangential to the circle, right? So the field on this particular on this particular armature is like this, right? Field is perpendicular to the armature. See, why is this curve shape? Pole is made, the air gap is maintained constant, right? Throughout the pole, the air gap is maintained constant. There is a reason to spread the flux uniformly over the surface of armature. To spread the flux uniformly over the surface of armature. So if you look at the magnetic axis, the axis joining both the magnetic poles, right? This is the magnetic axis. This can also be called as direct axis, D axis. This is D axis, right? And the axis exactly perpendicular to the D axis. Axis exactly in quadrature with the D axis, that is called as quadrature axis. This is Q axis. This is D axis and this is Q axis, right? So see here, the main field flux is from north to south, right? Main field flux is like this. So if it is a generator in which the rotation is clockwise like this, the velocity is tangential at any particular direction. See, this is the direction of flux. You can say flux density, right? The flux density and velocity are perpendicular to each other. What about the induced EMF? Tell me about the induced EMF. Use right hand rule. Is this is a generator? Apply right hand rule. See, the velocity is given by this. The flux is given by this finger. This finger will indicate the direction of current because of induced EMF. Because of induced EMF, the direction of current will be like this, which means into the plane of the board. This will be a cross. If it is cross below the north pole, below the south pole, it will be dot. You can check by applying right hand rule. You can check, right? So you have many such conductors below north and south, right? All cross in the conductors below north and all dot in the conductors below south. All cross in the conductors below north and all dots in the conductors below south, right? The armature is forming an electromagnet. See, the flux direction of armature flux will be like this. See, this is phi m main field flux and the armature flux will be like this. Armature flux is this phi a. What about the resultant? This is the resultant flux. You can call it as phi suffix r. See, you can see the main field, under the main field, the flux has to be in this direction along the direct axis, but the resultant field is distorted, which means it has cross magnetized. What happened? Cross magnetization took place. This is because of what? Armature current, right? This is because of armature current. Armature flux के वजह से ये cross magnetize हो गया. This has become cross magnetized, which means if the field is cross magnetized, right, the EMF induced will also be distorted. The field is distorted, the EMF induced will also be distorted. I'm saying it in short, I'm not expanding it much, right? So EMF induced will also be distorted. If the field is undistorted, the EMF induced will have a purely trapezoidal shape like this, pure trapezoidal shape like this. EMF induced will have a pure trapezoidal shape, but because of this, as there is distortion in the field, right, the trapezoidal shape gets distorted and this is the EMF shape which you are going to have, right? So this has more DC value. You have studied in signals, right? This will have more DC value, this will have less DC value. Because of this distortion, it will have harmonics, right? If there are harmonics, see armature, this is always laminated in DC machine, right? Because this induces harmonics, right? So because of these harmonics, this entire thing is rotating in a stationary field, which means there is relative motion between magnetic field as well as the iron core. Whenever there is a relative motion between magnetic core and magnetic field, there will be eddy currents and hysteresis loss in that, right? So harmonics increases, iron losses will increase. So these are the negative effects, adverse effects of your armature reaction. Now see what happened. The cross magnetization has took place. So what you have to do is you have to rotate the brushes, because previously this was the magnetic neutral axis. See, along this axis you had a magnetic flux component, magnetic field component. Along this particular axis, this vertical axis, you did not have any magnetic flux component, which means this is magnetically neutral. This axis was magnetically neutral. So now this magnetic neutral axis has shifted. See, axis perpendicular to this was magnetic neutral axis. Now the axis perpendicular to the resultant field will be the magnetic neutral axis. This will be the magnetic neutral axis. New MNA. Right? Previously Q axis used to be magnetic neutral axis. Right? So you have to shift the brushes, because till here crosses will be there and till here dots will be there. Right? The current is changing from cross to dot, which means the current direction is changing, right? You have to change the brush position, right? See, armature flux is this much. Because of this much armature flux, the armature reaction is this much cross magnetized. If armature flux increases, let us say armature flux increases, how can you increase the armature flux? If you increase the armature current, if you put more load on the generator, armature current will increase, obviously. If armature current increases, armature flux will increase, right? What happens to the resultant flux? Resultant flux angle has changed. Again, the angle of MNA has changed. New MNA is going to be perpendicular to this. MNA is going to be perpendicular to this, right? So you have to shift the brushes as the load is varying. That is not always possible, right? You have to think for automatic compensation. See, as the brushes are, you you have to hire a person and you have to tell him, if this much is the armature current, rotate the brushes by these many degrees. If this much, if the armature current is some 50 amperes, rotate the brush by 30 degrees, right? So this is not possible always. The load is completely dynamic, right? So to provide automatic compensation to armature reaction, we use compensating windings, right? See, armature flux is in this way. So we use compensating windings and we will cancel out the effect of armature flux. How to cancel out the effect of armature flux? We'll calculate. I'm not saying you how to calculate, as this is a short session, right? So we'll put compensating windings. See, a flux which is like this. This is created because of crosses here and dots here, right? This is armature flux, and compensating flux should oppose this particular flux. Compensating flux should oppose this flux, which means cross should be here and dot should be here. Yes or no? If cross is here and dot is here, use Oersted right hand thumb rule. This opposes this, right? So this is compensating flux phi c. To create a compensating flux, what you should do is you have to use this set of winding. You have to use a winding which is of this type, and the current which is flowing in the armature should flow in this particular winding, so that automatic compensation takes place. See, here you will place compensating windings. This is generally present in large DC machines only, as cutting slots on the pole faces is very a difficult process. It costs you much. It will cost you very much, right? So you will cut slots on the pole faces, and on the pole faces what you will do is you will insert some windings, and within these windings the current that flows is exactly opposite to that of armature current, and the mmf, armature mmf, will be exactly equivalent to this mmf, right? See here, therefore the current that should be here in this is crosses at this point and dots in this, crosses in that and dots in this, right? So what happens is this armature flux is countered, exactly countered, automatically countered. This is compensating flux. If they both cancel out, there is no distortion in the resultant flux. Resultant flux will be along the direct axis, right? So चाहे आप कितना भी कोशिश कर लें, आर्मेचर रिएक्शन को जीरो तो नहीं कर पाएंगे. It is not possible to make it zero, right? It is not possible to make the armature reaction completely zero. That is not possible, right? So even after doing this much area will be left unaffected, right? Because of this, some area is left unaffected, which means field is still distorted in this particular area. In this particular area, the field is still distorted. So to overcome this distortion, right? See, what we have to do is I will show you how the current direction changes during commutation. How commutation takes place. This is a winding under the influence of north pole, let us say, and there is one more winding which is under the influence of south pole, right? So the movement is like this. The conductors, or else you can say the coils, are moving from north to south. The movement is like this, right? So these are the commutator segments. The current under the conductors, which are under the influence of north pole, are like this. Let us say, just for example, this is some IA by A, and this is some IA by A. In south, in the coils under south pole, the current direction is different, right? So when this conductor is moving from the influence of north pole to south pole, the direction of current that is flowing in this particular coil has to change, right? Coil's direction has to change because of armature reaction. What happens is the influence of north pole increases, influence of north pole is extended towards the south pole, like this, let us say, right? Which means till here north pole's influence is present till this point, which means the EMF has to be zero at this point. This is the magnetic neutral axis. At the magnetic neutral axis, the magnetic flux density is zero. If flux density is zero at the neutral axis, EMF will also be zero because E is dependent on phi, right? Flux density is zero. So when it is moving from north pole's influence to south pole, there is a zero EMF point you have encountered here, but that is not becoming zero because of extension of the influence of north pole, because magnetic neutral axis shifted, right? So इनमें अभी भी इंड्यूस हो रहा है, नॉर्थ पोल की वजह से कुछ EMF इंड्यूस हो रहा है, right? Some EMF is inducing in them, right? So to place the brushes at the same position as the Q axis, right, we have to nullify the EMF under the conductors here in this region. Whatever the conductors we have to nullify the EMF in them, right? We have to nullify the EMF in them. So north pole's influence is extending till here, so we'll keep a south pole here. We'll keep a south pole which will exactly compensate for north pole's influence, right? We'll keep a calculated number of turns on this south pole, and those turns are connected in series with the armature. Similarly, the compensating windings are also connected in series with the armature so that armature current flows through them. The MMF is calculated, interpolar MMF, as well as the compensating winding MMF is calculated. Similarly here we should have to put a north pole to nullify the effect of the influence of this south pole in this region, right? So that commutation takes place properly. There is no EMF induced in that particular coil which is exactly at the magnetic neutral axis, right? Is it clear? I don't remember who had asked me. Is it clear to you? If find inductive KVA and conductive KVA in auto transformer, how will we find? Mahesh, see, the basic thing lies here in understanding what is inductive KVA and conductive KVA, right? See, there is no electrical isolation between primary as well as secondary, right? Whenever there is no electrical isolation between primary as well as secondary, there is some current that is passing from the primary to the load directly, right? See, this is your auto transformer. I'll just draw it here. This is your auto transformer, and this is the load terminal, right? So this is supplying the entire load KVA that is demanded. Load ने जितना KVA demand किया उतना source से supply हो रहा है. Source is supplying that much, right? So there is no electrical isolation between secondary and primary. Let us say this is 100 volts and this is some 200 volts, right? So this 200 volts winding is passing some current through the load. This current through the load is directly from the source, right? Some of this current is directly from the source, which means 200 volts multiplied by this current. This is conductive KVA. 200 volts multiplied by this current is conductive KVA. Whereas the remaining KVA, right? Total KVA minus conductive KVA, you will get inductive KVA. That's it. Is it clear, Mahesh? Right. Sri Rama, please post your doubt again. Your doubt, uh, it went up and I cannot read it clearly. Please post your doubt again. Meanwhile, I'll just erase the board. Please post your doubt. So if we have more time to explain armature reaction, I think everything would be clear. How to calculate the compensating MMF and how to calculate the interpolar MMF. Everything would be clear. But in short time, I've explained as much as I can. Right. Not sure if it comes under mechanical machines. If possible, can you please explain about mutual inductance? Different dot conventions in case of multiple coils in series and parallel connections. Uh, yes. So see here. See, dot convention is quite simple. Whether it is series connection, parallel connection, whatever it is, let us say it is some series connection. And there is no connection also. Even if there is no connection, you can understand dot convention very simply. See, let us say we have a transformer core here. We have a transformer core. And the primary winding of the core is like this. The secondary winding is like this. This is the secondary winding. Right. So if you are applying a sinusoidal voltage across this primary winding, you are applying a sinusoidal voltage. Because of this, the current is flowing like this. If a current is flowing through this winding in this manner, please go through Oersted's right hand thumb rule, how to apply Oersted's right hand thumb rule to obtain the direction of flux. See if dotted are added. See, the direction of flux is like this. This is the direction of flux. Direction of flux, I'm giving the arrow, right? So because of this particular flux direction, see if the flux is in this particular way, right? So what should be the EMF induced? What should be the polarity of EMF induced across this particular coil in order to satisfy Lenz's law, right? The EMF across this particular coil should be positive here and negative here. Why? I will tell you. See, you have connected a load here. Let us say you have connected some sort of load like this here, right? So the flux produced because of the secondary current should oppose the flux produced because of primary. If it is increasing, it should not let it increase. If it is decreasing, it should not let it decrease. That is what Lenz's law says. What Lenz's law say? What does Lenz's law say? Lenz's law says effect opposes the cause. In short, I'm just saying effect opposes the cause, right? So who is the effect here? Effect is this flux, right? No sound. Am I audible now? Please confirm. Everyone, please confirm. Am I audible or not? Yes, Bhagishree, it might be a problem with your configuration. Please reload the video. See, effect opposes the cause. This is what Lenz law says. See, flux because of this is in this direction. The counter flux developed because of the load in the secondary side should be opposing this flux, which means the direction of flux should be like this. Flux should be like this, right? So in order to get a flux like this, what should be the direction of current? Direction of current should be like this. Current should enter into this terminal, right? If current enters into this terminal, because of current entering into this terminal, you will get a flux opposing this particular flux. So if current is entering through this, it means it is coming out of this. To drive this kind of current, to drive current in this particular direction, EMF should be positive here and EMF should be negative here, right? Through a load, how does the current flow? Current flows from positive to negative, right? The EMF induced because of this main flux will oppose the sorry, the EMF induced because of this main flux will be in such a way that it will create a current which will oppose the main flux, right? That is what Lenz law says. So if you want to represent this configuration many times, right, you cannot always draw this core and windings and all, right? That kills your time. So to save time, we have come up with a simple representation. To save time here, we have come up with a simple representation, that is dot representation. See, if it is an iron core, we'll just draw two lines to indicate that this is an iron core, right? See, if there is a dot at the primary winding here and I'm applying a positive voltage like this, because of this positive voltage, what happens? Current enters through the dot. Current enters through the dot, right? If current enters through the dot, if current enters through the dot, a positive EMF is induced at the dotted terminal of the other winding. A positive EMF is induced at the dotted terminal of other winding. EMF is reversed in direction. Tarun Manoj, EMF, I'll tell you when EMF will reverse and what is question block in the screen. I'm sorry. Right. So when EMF direction will reverse, I'll tell you. So see here, the dotted terminal will have positive voltage induced. See, irrespective of the voltage here, if the current enters the dotted terminal, if the current enters the dotted terminal, voltage will be positive here. So this particular frame can be indicated by this dotted configuration. This particular frame can be indicated by this dotted configuration. If we have the sense of the winding changed, we have changed the sense of the winding. See here now. Sense of the winding is somewhat like this, right? This is the primary winding, and the secondary winding is reverse when compared to the previous case. इस केस से कंपेयर करो, ये इस बार रिवर्स. This is reverse this time, right? So in this particular winding, to oppose the main field flux, how is the main field flux? Main field flux because of the primary winding is like this, and to oppose this flux, we should create a flux in this direction, right? So to create a flux in this direction, to create a counter flux in this direction, right? The current should flow in this direction. Yes or no? The current should be into the winding in this manner, right? So to establish a current in this particular direction, positive should be induced here and negative should be induced here. This should be the EMF. Yes or no? Right? To drive a current in this particular direction through an external load, the direction should be like this, right? So to represent this particular frame, we can use this convention. See, dot here and dot here. Therefore, as current enters into the dotted terminal, you will see a positive voltage induced in this, right? When two circuits are magnetically coupled, right? When two windings are magnetically coupled, if the current enters through the dotted terminal, there will be a positive voltage induced across the dotted terminal, right? This is what is dot convention is. You can extend this dot convention to whatever circuit you study, right? आप जो भी सर्किट के बारे में, सीरीज सर्किट हो, पैरेलल सर्किट हो, if it is a coupled circuit, you can extend that. See, auto transformer is nothing but this kind of transformer connect these windings of two winding transformer connected in series, right? So if you connect like this is an auto transformer which we have seen previously. The configuration of this particular auto transformer is this dot here, and the second winding is like this dot here, right? We have seen this kind of configuration, right? This is nothing but series coupled circuit, right? So the voltage depends on across what two things you're taking the voltage, right? So parallel coupling, series coupling, everything is possible. You can add these two also. This is parallel coupling, right? So now you can just extend this particular dot convention. This is the basic dot convention actually, right? You can extend this to any set of circuits, whether it is parallel or series. Is it clear? Someone asked, I think Sri Rama has asked it. Is it clear till now? Any doubts in this? Any more doubts? Yes, got your point, Sri Rama. Just see, I've given you the basic idea. You please go through the derivations, you will completely understand it now, right? So you will be having series inductance or else series coupled uh, inductance as well as parallelly coupled inductance and all. They'll come under networks actually. So you please go through them, right? You please go through the derivations of them, and no need to worry, as those things are now removed from gate syllabus. Those are actually removed from gate syllabus. Magnetically coupled circuits are not there in gate syllabus, right? So thank you. That's all for today, and we'll be having the remaining in the next session tomorrow, right? So your appreciation and your if you praise us, that will motivate us to bring out more such videos through our Gate Academy, through the Gate Academy channel, right? So please subscribe to the Gate Academy channel and share the channel with your friends, and click on the notification icon, that is the bell icon, to get instant notifications of the upcoming videos. You'll have many such score booster sessions and many such videos, right? To get access to all those free lectures, you please subscribe to the channel.